Yeah, I think so. All right, so let's do some definitions. I think it's high time you understand the title of the course, right? The other thing I like about it is that I get to face this way instead of you seeing the back of my head the whole time. Okay. All right, so we're going to be talking about differential equations in the course, nonlinear differential equations in general, right? So all right, so our basic building block is going to be a differential equation that looks something like this, a control differential equation, okay? So x dot equals f of x u. All right, so let's just break this guy down, just make sure we're all on the same page. X is what we're going to call the state vector of the system. So that could be, let's say, the position of my elbow, the position of my wrist, the robotic arm, the velocity of my elbow, the velocity of my wrist. Okay? U is going to be my control inputs. So maybe it's the torque at the elbow from a motor. And at the wrist. Okay? These are going to be vectors, right? That means f is potentially a vector valued function. And then x dot is the time derivative of x. So what this function tells me is how x evolves in time given where I am right now and what control I'm applying. So x dot, just to define it, is dx dt, the time derivative of the state vector. Okay, so like I said, the only thing I don't like about this is that this is going to go away in a second when I want to write more. But we're recording it, so we'll put them up, and the lecture notes have all these equations in them too. Okay, so in particular, we're going to look at particular forms of f that we care a lot about. Okay, so in particular, we're going to focus on mechanical systems. What happens? Why do I highlight mechanical systems? Well, mechanical systems have a lot of structure to them. You know, they come out of F equals ma. That they're almost always second order systems. So so what does that mean? That means I'm gonna use a little bit more notation. I'll be specific, and I'll say Q is going to be the position vector. Q dot is going to be my velocity vector. So my state vector that I wrote on the last equation is going to be the accumulation of Q and Q dot. Okay. The position vector, I mean the joint angles. If there's a slider, it doesn't have to be an angle. It could be a length if it's a prismatic joint or something like this. But these are the things that identify the position of the robot in space, and its time derivative is in Q dot. And then really the dynamics that of interest here are really how the dynamics of how the velocity evolves is trivial in a second order system, but what I care about is the second derivative here, how the accelerations of the system happen as a function of Q dot, and U, right? So this is just a slightly more specialized form of what I wrote on the first slide. And actually, because we care about mechanical systems, we're gonna zoom in even a little bit more, put even more structure in. Okay, let's go ahead and assume that U enters in only a very particular way. Okay, so we're gonna think about systems that have this form. These are the control affine systems. Okay, so this is more specific than this. It says that Q can still enter in some general way. F is a sort of a catch-all. I can write anything inside my map F. But this says that U can only affect the accelerations in an affine way. It's got a linear term and potentially a constant term with respect to U. Okay? And we're going to justify that by looking at the way the equations fall out of our mechanical systems and seeing that if torque is an input, for instance, the accelerations are always affine in the torque. Okay? And this structure is going to make our lives better. We're going to exploit it in many different algorithms throughout the term. It doesn't always exist. Airfoils on quickly moving vehicles might be a counterexample, although you can linearize them. But this is a structure that we're going to try to exploit whenever possible. Okay, so that makes sense. This is all just a more specific form of the x dot equals f of x u. Okay. All right. So now let's make our definition here. So using this second order system, a second order system like this is, I'm define fully actuated first, is fully actuated. Hopefully you can maybe predict what I'm going to say. If F2, if this guy here, F2, Q dot, is full rank. What matters is it's full row rank, right? Right? So what does that mean? Well, let's be a little specific here. So let's say I have n positions I'm trying to control in the system, and I have the dimension of u is m. I have m inputs, so I have n positions, things I'm trying to control, m inputs, control inputs, right? And so f of 2, since it's going to map u to q double dot, f of 2 is a vector, it has to live in, it's a matrix, right? An n by m matrix. And I'd like for the rank of f2 to be greater than or equal to n. That implies the system is fully actuated. We're going to see why in great detail, okay? But first, let's make sure that the algebra is clear, okay? So the rank of this matrix here has got to be greater than or equal to n. Now, a couple things to note. By given this definition, really, I want to be able to say that a system is fully actuated in some state. So the answer of is the system fully actuated or not is state dependent potentially. It could be that for some positions of the robot, I'm fully actuated. In other positions of the robot, I'm not. Right? It could change depending, because f of 2 will change as a function of q and q dot. So it could lose rank sometimes. Now, in most cases, I think every case that we'll talk about in the class, it's going to turn out to be a global property of the system. But it could, it depends on well, that's not true. We'll hit examples where it will be sort of a state-dependent property of the system. Okay, so it's a function of q and q dot. And the obvious sort of follow-on here is the system is under-actuated. No hyphen. We've coined a word. All right. If the rank of F2 Q dot, it's under-actuated in that state if it's rank deficient, right? All right, so hopefully that sort of, just by the algebra, makes sense, but why is that such a big deal, right? Why make a course with that in the title? All right, here's the most important thing you're going to get out of the lecture today, right? So there's two types of systems in the world, I guess. There's linear systems and there's nonlinear systems, right? So Professor Magretsky always says that's like saying elephants and non-elephants, or it's kind of a ridiculous thing to say. But the fact is, most of the courses you'll take in control, even at MIT here, thinks a lot about linear systems, right? I can write, if I were to write my x dot equals f of x u and it had a linear system, then it was a linear system, then I could write it in this form, ax plus bu. That's the state space form for a linear system, right? The nonlinear systems are my more general, which include the linear systems, although the name is, I didn't name it, right? Right, that's the more general form, but the linear systems are special, right? Why are the linear systems special? There's something you can always do for a linear system that you can't do for a nonlinear system, which is you can solve that differential equation, right? You can integrate forward in time. The solutions have e to the ax in them. You've seen them before, okay? I can tell you what's going to happen. If you give me a u input, I can tell you what's going to happen in x in the future. Okay? We're going to write down very simple nonlinear systems, extremely simple nonlinear systems, very simple forms of that, where you won't be able to do that. Okay? That is a huge, huge defining difference. And what it means is that in practice, the world has bared out incredibly, amazingly strong theoretical results on how you can control linear systems. You can talk about the robustness in linear systems. You can optimize the response of linear systems to n degrees in almost any objective you choose to write down. Okay? Not every, but a lot of them. And if you crack the nonlinear control textbooks, you'll be disappointed. There's just a lot less that you can do with the general form of nonlinear systems. Okay? So these are categorically sort of extremely different situations. If you can make yourself into a linear system, then you're in a good place in terms of control. And if you can't, you've got to solve a harder problem. So the big deal about the under-actuated systems is that you have to think about the nonlinear dynamics. You can't make them look like a linear system. And the way you have to see that is with this idea of feedback linearization. One of the great things about the course is everybody's coming from lots of different backgrounds. I hope at least some of you are sort of, let's say, computer scientists that may not have thought about, that might be thinking about robotics a lot, but maybe haven't thought about dynamics a lot. And some of you are mechanical engineers or aero engineers or otherwise sort of very familiar with dynamics. If that's the case, then I hope still I'll say something a little bit different about the way different than the way you normally think about dynamics. The goal for today is to make sure we're on the same page. We all understand sort of the basic concepts that we're going to use in the course for nonlinear dynamics. But really the goal is to sort of stoke your intuition and make you think about the dynamics the way I hope you're thinking about dynamics in the course. I want you to love dynamics, okay? So we can actually do a lot of it if we think about even just the dynamics of the simple pendulum. We're going to spend a lot of today thinking about just very simple systems like the pendulum. So let's start by drawing our simple pendulum here. So simple, when you're thinking about these models, there's lots of things that simple might mean, but simple typically means you're using point masses instead of sort of inertial models. So So I've got literally a pendulum with all its mass concentrated at the end of the pendulum here, with an ideal rod of length L, and I'm going to parameterize it with the coordinate theta from the bottom, and I've got gravity pointing down and mass L, M, and basically the simplest possible robot I could ever describe, right? Because it's so simple, we can generate the equations of motion in a heartbeat. So the total energy of that system is 1/2 mv squared, which is v in this case is L theta dot, so L squared theta dot squared. That's my energy. The total potential energy, it's sort of weird. I'll make it a negative energy just because it's hanging. I'll have zero potential being at the sort of at the base there. So I'll do negative mgl cos theta as my total potential energy. And if, like I did in the appendix, which I don't expect you to be able to do, but I just want you to know that it's easy to do if you want to. If you want to get the equations of motion, the differential equations that describe that system, you can just assemble the Lagrangian, which is t minus u. You can pump it into the Lagrangian differential equation. That's a dt partial L partial q dot I minus partial L partial q I is some general force I. In this case, we just have one q, right? So in this case, our q is theta and q dot is theta dot, right? And we get out the equations of the pendulum, which is gives us ml squared theta double dot plus mgl sine theta equals this q. Q is sort of a generalized force, a force input in generalized coordinates. So when we're thinking about pendula hanging down like this, we're going to think about a couple different sort of generalized forces we'll put in the system. We'll put a torque at the base here, a torque here, and we'll think about a damping too. So in our case, we'll say Q is going to be some torque input. We'll just call it U directly. That's what we've been calling our inputs to the system. And then we're going to think about some damping, some friction in the system, because if you have a real robot, you're going to have some damping there. And the simplest model of friction in this case would be which would be a linear function of the velocity. We'll do more complicated models later, but this will be our damping. This will be our input, U or tau. So if you have a motor at the base. Okay, so in total, we'd like the equations of motion we're going to think about today to be this sort of canonical ml squared theta double dot plus b theta dot plus mgl sine theta equals u. This is our canonical pendulum differential equation. Okay, so you've probably taken differential equations, and you know that the standard thing to do once you're given a differential equation, if I have my canonical differential equation here, it's a second order differential equation, ml squared theta double dot plus b theta dot plus mgl sine theta. I'm just rewriting it at the top here for you. Okay. Then the standard thing you do in your diffie-q class would be to solve the differential equation, right? So solving the differential equation means if I give you the initial conditions, for instance, in this case, I'd give you theta at time 0, right? And I give you theta dot at time 0. Then what I'd ask from you to solve the differential equation is I'd like you to give me theta as a function of time, right? That's the standard ask for a differential equations course. So unfortunately, the answer to this question is relatively unsatisfying. Okay, so this is really one of the simplest differential equations I could write down, and I can't. Well, I sort of can solve it, but you wouldn't like what I'd write down, and I can only solve it if b equals 0. And when b equals 0, I have to use elliptic integrals of the first kind, and it's just not useful. And then if b is not equal to 0, I can't even give you a closed form answer. Okay, so. What the heck? I thought it seems like we've solved more complicated differential equations than that in your diffie-q class. But the big difference is the fact that this sine theta entered in there. So it's not a linear differential equation, it's a nonlinear differential equation. And it's not meaningful to solve. It doesn't have a closed form solution in the general case using within closed form. So that's a bummer. It seems like we're hoping to do more complicated robots than this, and already we're stuck. But it turns out you can still do a lot of things with this, of course. So one of the messages for today is that I can basically completely understand the behavior of this system, if I'm willing to ask slightly different questions. Okay, so asking exactly where theta is at time 6.2 is sort of not the right question. That's a hard question to answer. But if you ask about what theta is as time goes to infinity, or what are the basic properties of a solution of theta, there's lots of things we can answer and can answer meaningfully, but it's just not using the traditional solve that differential equation tools. Okay, so that's what you have to get used to when you start doing the nonlinear differential equations. You have to start using different tools, right? So for instance, if I take this system and I ask you what is theta at time infinity, what would you think is the obvious answer? Yeah, it's down at 0, right? Especially if b is greater than 0, right? If I've got some positive damping in the system, then eventually I'm going to run out of energy and stand still. You all know that, and we're going to have lots of ways to compute that as using sophisticated tools for more sophisticated equations. But we're going to do it we're going to see for a class of differential equations, there's very intuitive tools that we'll use today in lecture to make sure we're all on top of it. Okay, so the goal is to interrogate nonlinear differential equations like this using some general tools, things that are going to work for the pendulum, but work for more complicated systems too. So what are some general tools? I mean, one of them certainly is the idea of linearization. Okay, so if you just care about the behavior of this system, let's say in the vicinity of some particular point, I could take that equation and I could linearize it, make an approximation of sine using a line. Okay. And then I get a linear differential equation which I could solve. And that's certainly one powerful tool that we're going to use for even complicated robots. Okay? So it's good for local analysis. Most of the time. There will be nonlinear systems where the linearization is not informative. But in general, it's good for local analysis. But you might miss the global properties. You might miss the good stuff, right? And the other class of tools that I want to talk about today are sort of a graphical analysis. Okay, and so there's a great book by Steve Strogatz, which is one of the recommended sort of optional additional readings for the course. But if you like the kind of tools we're talking about today, this is sort of a one lecture channeling of Steve Strogatz's version of what he teaches a semester-long course on this stuff. It's a beautiful. I see the book right there. It's a beautiful course. It's a beautiful topic. Okay, guys, welcome back. Today's going to be a fun day. I think we've got. Give myself a little more slack on that. Some of you have seen sort of the CS side of this before, the dynamic programming side of this before. But even for those of you that have, I hope that you'll see it through the lens of dynamics today. And for those of you that haven't thought about sort of optimal control in terms of dynamic programming, then what we're going to see today is some very simple to understand methods that are actually going to do beautiful things to the dynamical systems we were talking about last time. So I hope that by the end you'll feel like you can write down very simple algorithms that really understand the dynamical systems that we were talking about and understand the nonlinear dynamics. Okay, so let me plug this hole in the floor. Otherwise I will. Okay. Let me just start by reminding you where we were last time, right? We were talking about the eyeball of the simple pendulum, right? So we had this simple pendulum system, and we drew the phase portrait of that system as theta versus theta dot. We talked about the stable, at least in the sense of Lyapunov, fixed point at the origin, the unstable fixed points at the upright. And for the undamped pendulum, right, if the equations were just ml squared theta double dot plus mgl sine theta equals tau, right? So I'll have a torque here. For the undamped pendulum, the orbits of the pendulum had this eyeball look to them. There's actually an important sort of magical orbit that visits the unstable equilibrium. It's called the homoclinic orbit. We'll talk more about that later, but there was other sort of simpler orbits inside the eyeball and more complicated orbits outside, right? Okay, and we talked about plotting this whole vector field. At any given point, I could draw sort of the instantaneous, the tangent of that orbit, really, as a vector by just plotting the differential equation as a vector-valued function. Okay, and then we talked about the thing I wanted to try to get across at the end was that control for a second-order system, let me put my colors to use here. My torque input can change that vector, right? And we're talking about, as a control engineer, you get to be sort of a puppeteer that gets to move that vector field around, make it, within limits, the torque, this would be positive torque, maybe this would be negative torque here, or I should say torque greater than 0, torque less than 0 down here, right? But by pushing and pulling on the torques, you get to change the way those vectors look, and then you get to change the dynamics of your system you're trying to control. Okay, so here's what I want to talk about today. I want to talk about, right now we've got a system that's stable at the downright configuration and unstable at the upright configuration. Let's see if we can come up with a good way of making it stable at the upright configuration. But to make it interesting, I'm gonna make sure that you've got some torque limits. Okay? So how are we the challenge here is, how can we stabilize the unstable fixed points? And I'd like them to be sort of very stable. I don't want them to just be, stable if I start very close to them. I'd like them to have a big region of attraction, right? Okay, so if you get to move all the vector fields around, then you might think, okay, well, my goal then is to, if I have my phase portrait here, I've got my unstable fixed point. What I should do is somehow change all of the vectors so they're pointing right at that fixed point. If I can move all the vectors around, if I've got this power over the vectors, then I should just be able to make that a big sucking sound and bring all the orbits directly to that fixed point, right? If you've got sort of arbitrary control, then that would maybe be what you'd like to do. But guess what? You're not going to be able to do that. Partly because you're only allowed to control the acceleration, and really you're only allowed to move. Control only affects the y component of the velocity of the vectors, okay? And if we have torque limits, then you'll have other reasons why you can't do that, okay? Right, so for instance, if there's some vector of the passive system right here, and if I can only add or subtract to that in the y direction, there's nothing I can do that make it point directly towards the fixed point. Does that make sense? And that's just, it's kind of funny to think of that in the plot, but what that is saying is that I can't move from here to here without having some velocity in between. I mean, that's just a function of it being a second order system. That's a very natural physical thing. Okay, so we have to do something more clever than that. So here's an idea, right, would be, which we've already talked about. Maybe we could do feedback cancellation, right? Right, so what if I did torque equals 2 mgl sine theta? Right, so that's a control system. That would be where the control input, the torque, is a function of the angle, of the current measured angle of the state of the pendulum. It's a feedback controller. And it's an interesting one. If I pop it into the equation, then what I end up with, if I substitute tau in here and simplify, what I'll end up with is a new dynamical system, which is just negative mgl sine theta, which is exactly like I inverted gravity. My g turned to a negative g. Right, so I inverted gravity with this. That will absolutely work. If you draw the face portrait of that, you could go through the exercise, but you'll get just the eyeball moved over. You'll have a new dynamical system which goes like this. And it just acts like the pendulum's upside down, right? If I have a little damping too, it'll slow down, right? This is the undamped one. The problem is that's potentially going to require ridiculous amounts of torque to somehow to cancel out gravity and act like not only that I'm going to go up here, but I'm actually going to go up as fast as if I was falling down on the other side, right? So it's going to require too much. If I have a torque limit, I'm not going to necessarily be able to do that. So for instance, I can just say, what if tau is got to be less than or equal to mgl over 4? That would be sufficient to break that. Somehow mgl is the torque required to hold myself here. Let me just take a fraction of that, and suddenly I can't invert gravity anymore, right? Okay, so we're going to be able to solve this beautifully by the end of the day. But it's actually surprisingly hard. It's actually, it's really difficult to think about how you should redirect these vectors and reshape that vector field, satisfying all these constraints, and moving this into a new dynamical system that's stable at the upright. It's really a subtle, hard problem. Okay, and we're going to ultimately
rely on the computer to do the work for us. Okay, so let's start that story. Okay, so the big idea for today is that we're gonna start talking in a language that we can turn into a program by describing our goals for the control system as an optimization, as an objective, right? So the big idea is I'm going to formulate the feedback control design problem. As an optimization problem. If I can write it down as an optimization, optimization is a great thing. We'll talk a lot about it in various contexts in the semester. Optimization is going to give me a very compact way to describe my goals for the system. It's going to be something that I'm going to be able to work with on paper. For some systems, I'll be able to just solve optimization problems in closed form for some systems. But maybe the point today is that optimization is going to be a very specific specification we're going to be able to give an algorithm and ask it to solve for us. Okay. So how do I formulate the feedback control design as an optimization? Okay. So somehow I need to associate value or scores with I need to somehow label an objective. So the way we're going to do it is we're going to say, given some trajectory of the system, so this is my shorthand for trajectory. So let's say, for all t in some interval x of t, okay, and this interval we'll see can be finite or infinite, but I'll put a star there. We're going to come back to what that means in a second. Okay, but I want some trajectory. You let the system run, and then when you're done with that trajectory running, I need to be able to give you a score, right? I need to be able to assign a score to that trajectory. Right, so just like the judges at the Olympics, right? So if the pendulum does something, I need to be able to put up a 9.7, right? My little guy holding up a sign, yeah. So every time the pendulum does something, I need to say, "Good job. Here's your numerical value," and that gives me something tangible then to optimize, right? Optimization can also take as a constraint that I'm only going to worry about some trajectories that have some constraints satisfied. So I could formulate something that I'm going to give you a score, and I'm going to tell you that, for instance, this was a constraint we've already seen, that tau has to be less than some tau max. Okay? So you could write down an optimization saying maximize your score subject to the constraint that tau is less than tau max always. You can also put down maybe more complicated constraints in some sense. You could say at x, let's say x equals 5. Figure out what you need to figure out optimization, but at time equals 5, or some final time, I'd like x to be at the goal. I can list different types of constraints, and we'll see what kind of constraints we'll be able to do. Okay, and then this notion of infinite, how would you score an infinite trajectory? We'll see more of this in a little bit, how that makes sense. But typically, the infinite means I need to be able to still assign a score in a reasonable way. So I want my score, for instance, to be finite, even if the trajectory is infinite. And it typically requires the system converging to some solution. So if it's moving around forever, maybe that's a hard case. But what I care about is that the score is finite, even if the trajectory is infinite. And often that implies that there's some convergence. That x and u go to some constant value, to some fixed point, for instance. And then it's easy to talk about an infinite solution. And we'll get into that as we see the exact formulations. Okay, does that make sense? The idea of just sort of giving a score for a performance of a robot, right? And then once you have this sort of formulation of giving a score, then the goal of the optimization in general is to find a control policy which in general is a feedback controller. You see my reinforcement learning background with when I use pi for my controller, Scott. And so in general, we've got some feedback controller that minimizes or maximizes my score. It's actually kind of funny, right? So there's two communities that work on these sort of optimization problems. There's the computer science community. You'd see it as a subset of machine learning. There's people that do reinforcement learning. Okay, in reinforcement learning, you give reward for your robot doing a nice thing, and you try to maximize your reward. If you're a control theorist, you penalize the system for doing something, and you minimize the score. So it's, I don't know, is the glass half full, is the glass half empty? But the control theorists penalize, and the computer scientists reward. But I'll be a control theorist today. So let's say I'm going to minimize my score, okay, and plus I have to satisfy all my constraints. All right, sometimes we'll be able to do this analytically, but more often than not, and even for that darn simple pendulum, we're going to have to do it computationally, okay? All right, but let's do one where we can do it analytically so that we can think a little bit more deeply about the way these solutions come about, okay? So,
okay. Now, it's important to note that these equations we've been working with, this g of s I is some min over a in a, g of sa plus j of the next s, right? We listed this as an algorithm, right? And then we gave the controller that you could extract from that algorithm was the optimal action is the minimizing a. It's the a that if you evaluate this for every possible action, you take the minimum one. That's my optimal policy, my optimal controller. Okay, so in discrete time, this was a beautiful algorithm, which we said had some nice properties. It meant that if I took an initial guess at my cost to go vector j, and I put it into this right-hand side, evaluated the minimum, and updated that guess on the left-hand side, that this was an algorithm that surprisingly converged. Okay, but it's important to note that this equation represents more than just an algorithm. It actually represents sufficient conditions. Okay, so if you tell me I have a controller that I believe is optimal, and you can produce a j, then I'm going to take that j and I'm going to put it into this equation, and if everywhere the right hand side equals the left hand side, if this equation is satisfied for all my j, then you've convinced me without doing any work except for verifying that you've got an optimal controller. Right? So this equation here represents sufficient conditions
for optimality. If you can give me a J that satisfies those conditions, then you've demonstrated that you've got an optimal cost to go. And if you have a pi that satisfies this condition relative to J, you've demonstrated you have an optimal policy, an optimal feedback controller. Okay, now this is a great start, right? This discrete state, discrete action, making everything turn into a grid. We know how to do dynamic programming on a grid extremely effectively. But it still left a lot to be desired because we had to do these approximations for the continuous time system. We had to even pretend that we had to find ways to pretend that our continuous system actually looked like a grid. Now it's important to realize that there are beautiful continuous time equivalents of these sufficiency conditions. Okay, so in continuous time, we have almost the same conditions, okay? But now the equations in continuous time and continuous state and continuous actions, right, where now my dynamics are x dot equals f of xu. Right? They look a lot like this, but they take a slightly different form. Now I have my sufficient conditions are min over u, g of xu, plus partial j, partial x, f of xu. Okay? And similarly, my optimal controller, as a function of x now, is the minimizing action. Okay, and if this is the optimal j, then there's a star here. Okay. So it turns out that the derivation of this, I'll give some references in the notes of how you can see this derivation. It's relatively straightforward to give an informal derivation. Okay, but basically, if I take the limit of this, if I change all my states to my discrete states s to continuous values x, my discrete actions a to the continuous actions u, and then I take a limit of this sort of update as time goes to infinity, then you'll arrive at this new continuous equation here. Okay, this is an extremely famous equation. It's called the Hamilton-Jacobi-Bellman equation. Right, HJB. And again, it's a sufficient condition for optimality. Okay? And we're going to use it again and again and again. Extremely powerful. Now, a few things to notice about the equation. All right? Now, this is a partial differential equation. Okay, what does that mean? That means that the equation here is defined, in some sense, my optimal cost to go j is only defined in terms of some equation that governs that's defined on its derivatives. Okay, so to solve this equation for j is potentially hard. To find some j which satisfies this equation everywhere is potentially hard. In the same way that I'd have to, if it was a differential equation, I might have to integrate from a differential equation. It's hard to potentially integrate that to a closed form solution. Here, I'd have to integrate over many dimensions, x, this partial, to get a closed form expression for j, and that can be very, very hard. Okay, there's going to be some cases where we'll be able to do it, but in general, this involves the solution of a partial differential equation, and it's a nonlinear partial differential equation. So a lot of times we're going to result in numerical methods even for this sort of continuous piece. Okay, now we can still immediately put it to use. Okay. So imagine I give you a controller. Okay, So let's take our double integrator example again. Where my dynamics were q double dot equals u. This time we'll say there's no limit on u. U can be any value. But let's solve an optimal control problem where my cost function is, let's say, q squared plus q dot squared plus u squared. Okay, so instead of bounding u to be within -1 and 1 like I've been doing before, this time I'm going to put a cost on u, okay, a quadratic cost on u. So it's better to have u close to 0, right? And if I apply force to my mass, remember u is the force on the sort of unit mass brick, okay? Right, the smaller my force is, the better, okay? And I'm going to still try to make it go to 0 by penalizing q being away from 0 and penalizing velocity being away from 0. Okay, so my claim is that I know the optimal controller for this, okay? And my claim is that the optimal controller is -q minus square root of 3 q dot, okay? That's my claim. And the way I'm going to convince you that this is actually true is I'm going to produce the following function. J of x is square root of 3 q squared plus 2q q dot plus square root of 3 q dot, okay? And this function now, if I put it into my claim is if I put this into the HJB equation, it's going to prove the optimality of this controller. So let's do it, okay? So given this j, the first thing we're going to need to do is to understand its partial derivatives. So this is going to be 2 square root of 3 q, okay, plus 2 q dot, partial j, partial q dot is going to be 2q plus, oops, I forgot a squared here, sorry about that, 2 square root of 3 q dot, okay? So I can write now my partial differential equation, my HJB. Let's first write the inside of it. So g of xu plus partial j partial q dot plus partial j partial q dot times q double dot, which is just u, right? This is the right-hand side of my partial differential equation. Let's plug in some of these values now. That gives me q squared plus q dot squared plus u squared. Partial j partial q, I can plug that in. 2 square root of 3q plus 2q dot q dot plus 2q 2 square root of 3 q dot u. Okay. All right, so this is my right-hand side, and now I need to take the minimum of this with respect to u. How am I going to do that? Okay. Well, it turns out this is a nonlinear function, of course. Finding its minimum value is potentially hard, but it's a very special quadratic function. It happens to be a quadratic function, and a quadratic function that's particularly simple. I know that it's going to be a convex function. So this is some function of u. If I were to plot this function as a function of u, then it looks like some quadratic bowl like this. Okay. So I'm going to be able to find the minimum value in this special case by taking the derivative with this respect to u, finding out where that's 0, and that's going to give me the minimum value. Okay? So let's take the gradient of this whole big thing with respect to u. Maybe I'll just shorthand it like this. I'll say the gradient of that whole big thing with respect to u is going to be, what, 2u, right? Plus this whole thing. 2 square root of 3 q dot. Plus 2q. Okay? All right, so now if I were to, this thing has to be equal to 0, right? That implies that the minimizing controller, what I'm calling u star here, if I take this to the other side, divide everything by 2, is going to be what I originally proposed, which is minus square root of 3 q dot. Okay, so in fact, the u that minimizes this equation here is in fact this u that I proposed. That's a good start. But even better now, we need to prove that that this whole equation equals 0. So let's substitute u back into this equation and see what we get. And it turns out if you do that, if you stick this whole thing back in, right here, into this, then you'll in fact see that this equals 0. I'm going to skip the algebra here, but that whole min over u put back in, that equals 0. So this, in fact, this function here proves the optimality of my controller. Okay, that's just by using the HJB sufficiency theorem. Which says that if I can write a cost to go function which has to be everywhere differentiable, okay, there's some technical conditions which are written carefully in the notes, okay, and I have a controller which acts to minimize this right-hand side of my Hamilton-Jacobi-Bellman equation, then I know that I have an optimal controller. Okay. It turns out, just for interest, why did I pick the no limit on u and the slightly different cost function? It turns out if you were to run the same test for the minimum time problem for the double integrator, we have a controller there too, right? And you can produce the cost to go function. In fact, you already know what that is. What's the cost to go function for the minimum time problem? Well, from a given state, it's just the time it takes to get to the goal for that state. So we have a function, closed form, for the time to go, in that case, of this function. And if you plug this in here, then you'll get that everything equals 0. Again, you'll get that all these conditions are met, with one small caveat, the fact that this time to go function is not actually continuously differentiable. So everywhere that this derivative exists, the Hamilton-Jacobi-Bellman equation is satisfied. So that's strong evidence that it's an optimal controller, but technically the HJB sufficiency theorem doesn't hold unless this equation matches everywhere, and we can't quite say that for the minimum time problem. But for this smooth version of the problem, it works beautifully. Okay, so we're going to work a lot with this Hamilton-Jacobi-Bellman equation over the next few lectures. It's sort of a beautiful thing to be able to write down such a simple. I mean, it's still a partial differential equation, but this is for something that captures the long-term dynamics of my the ability to have an optimal controller which minimizes some long-term cost with a simple equation that involves a partial derivative for sure, but otherwise very simple entries in the dynamics and cost, right? This is a magically simple, beautiful equation. One of the things that makes it a little bit more ugly than even just a standard partial differential equation is this min over u. In general, that minimization over u might be hard to do analytically. We lucked out and did it analytically in that simple example, but this can potentially be a hard, even a source of discontinuity, but a difficult thing to solve. Okay, there's one very important case that we'll use again and again, where you can solve away min over u. So let's make sure we see that and think about that. Okay. All right. That's my HJB. Now, there's an example. There's a class of problems that we that we're going to care deeply about where you actually can solve away the min over u. Okay, so let's think of the examples we've been talking about in class. A lot of times, F, remember from the very first lecture, we said most of the systems we care about are going to be second order systems, but they're also going to have a particular important structure, which is that they're control affine, right? So a lot of times you'll be able to write the system as F1 of x plus F2 of x u, okay? So this is control affine. Their systems are arbitrarily complex in x, but they only enter in an affine way in u, okay? So we'll restrict ourselves to that set of dynamics first. And then the cost function is something we get to choose, right? So in general, we've seen a couple different options for cost functions. We've seen something that just penalized time to goal, and we've seen this sort of quadratic cost on u. So let's think more about the quadratic costs on u, right? So in the general form, we'll say that g of xu can be some complicated function of x, but let's make it just be a quadratic function of u. Okay? My claim is if we do that, then even if f is very complicated in x, it's relatively simple in u, and we're going to be able to solve this away. And doing that's going to give us a little bit more insight into this continuous time optimal control problem. Okay, so let's see what it looks like. If I write it out, I have a min over u, g1 of x plus okay. Now again, I should be careful here. This isn't just any quadratic form. I'm going to, since I get to pick the cost function again, I'm going to make sure I pick an r, which is not only symmetric, but is strictly positive definite, okay? Which means that this, again, is a quadratic function in u. If I were to plot in any direction of u here, okay, u1, u2, let's say, it could be, it's potentially multidimensional, I'm going to still get a quadratic bowl, right? Now in higher dimensions. Okay? And since r is positive, I know that that bowl is pointing up. So again, I know my same trick of taking the gradient and looking where it equals 0 is going to be the minimizing u for this equation, right? And this equation only has a quadratic dependency on u here and only a linear dependence on u here, okay? So let's do the same trick again. Let's take the gradient of that whole big right-hand side, okay, here, and with respect to u, and you'll get used to these matrix gradients, but in the case where r is symmetric, I get back u transpose r, okay, here, and then this whole thing here, the only term that's left is partial j partial x f2 of x. Okay, so it turns out to be something simple. And I want to set it equal to 0, find the places where that's equal to 0. And if I solve this away, if I subtract this to the other side, then I get, and I'll take a transpose just to get u to be a column vector again. And I get negative r inverse, remember r was invertible, so that's good, f2 of x transpose, partial j partial x transpose, okay? So if in this special case of quadratic cost on u and control affine dynamics, it turns out I can find the optimal u in closed form, okay? And then I could stick it back into this equation and work with it algebraically, and now I have a new equation which doesn't have this min over u. It just, my now conditions for optimality are, well, it's a big thing. I'll start writing it out for you, but times r inverse again leaves me with just one r inverse. but this, and you can finish with this, inserting that in, okay? You get a big complicated expression with j's appearing even more places, but the point is it has no u and no min over u. So this is potentially something that's closer to smooth computation. But what I really want to zoom in on, and to make sure you have some intuition for is what this optimal control looks like in terms of j, okay? So let's think about this. I've got some cost to go function over my state space, okay? I have now x1, x2, my cost to go function, j of x, right? And it's some complicated function, right, that may do lots of different complicated things in multi-dimensions, okay? Right? But wherever I am, the optimal controller, given this cost function, is actually fairly simple, okay? Given this complicated function j of x, partial j partial x is the gradient, okay? So the first thing you should see here is that you see negative partial j partial x. That says, go downhill. Okay, so instantaneously, if I know what the cost to go is at my current state, and I know what the cost to go is at all my neighboring states, then the first thing I should try to do here, what this math has told us, is that I should try to go downhill, negative j x transpose, okay? But I can't go necessarily, I don't necessarily have to go directly downhill, I have to somehow go downhill in x. So I have to map my desire to go downhill in x back onto my actuator coordinates. Okay, how do I do that? Well, F2 is what maps control inputs to actuator space, right? So this thing, negative F2 x partial j partial x, is go downhill, in actuator space. Right? Find the control inputs that's going to go downhill. And then I've only got one extra term here, which is this negative r inverse on top of that. And what does that say? This is weighted by my relative costs on action. Right? So if I used R to say there's some controls that are different, very different than others, right? Let's say I said, what would it mean to have R be, let's say, 10, 1, 0, 0? That's telling me that I incur 10 times more cost when I use actuator 1, right? This would be the same as now U transpose RU this would be the same as writing 10U1 squared plus U2 squared, right? This is saying that it's 10 times more costly to use actuator 1 than actuator 2, and this R inverse is just mapping, is the result of that weighting pushed back through, okay? So the picture I want you to have in your head is if you can somehow magically come up with this cost to go function, J, in a continuous sense, in the continuous state, continuous action, continuous time, the optimal controller for this formulation is to go downhill as fast as possible, modulated by my control inputs, and then weighted by my relative costs of the different terms. Okay, that's a very important picture to have in your head, is that your goal in life is to go downhill on the cost to go function. Okay, we're going to see a couple very, very important examples of this. In the next lecture, we'll see that if G is also quadratic and x dot is linear, then we're going to be able to solve this exactly all the way through and find a J that works. But in general, we're not always going to be able to do that. Even for this formulation, this is sort of a half solution. Okay, the theory of the HJB equation and how you use this in an algorithm, how to use this continuous form in the algorithm, is rich and varied. Okay, in general, you get into topics of let's say using function approximators to approximate J, and we run out of theorems fast, but we have a number of algorithms that work fairly well, and that'll be something that that's a set of ideas that we're going to revisit at the very end of the course when we start talking about reinforcement learning approaches to optimal control. But for now, the most important part of this, most important message for the moment, is that the dynamic programming algorithm we gave last time is more than an algorithm. It's a sufficiency theorem, which tells me a way to verify an optimal controller and an optimal cost to go if given. If it satisfies this equation in continuous time or the value iteration equation in discrete time, then I can be convinced that it's optimal. And in continuous time, we have a beautiful mathematical object that we can work with, and we'll work with in the next few lectures. Okay, let's, you ready, Ani? Yeah? Let's go ahead and get started. So, just for context, we've actually done a lot of the sort of preliminary work we had to do. We've talked about the manipulator equations. We've talked about feedback linearization. We've introduced sort of nonlinear dynamics. We've talked about optimal control. That's just 4 lectures, right? So, and dynamic programming. So now we start actually looking at more advanced systems. We've been thinking a lot about the double integrator, the pendulum, and we're going to start sort of ratcheting up the complexity a little bit, and looking at some of the model under actuated systems this time. We're actually, you'll see, we'll go back and when it makes sense, we'll go back and we'll look at the way things play out on the pendulum or the double integrator or something, just because that's such a system that those are systems that we can really understand, and we can understand the new algorithms on these old systems, and that's very nice, and see how they compare to our, dynamic programming type algorithms. But today we start talking about the model systems, right? So, model under actuated systems. So basically, if you look at the literature in the controls world and the robotics world on sort of the standard and novel control techniques for this type of robot, there's a handful of examples that everybody uses, right? There's a handful of examples that are well understood, I would say. Sometimes they're well understood that we don't have a good solution, but still, there's just a handful of examples. So some of them you'll have recognized, you recognize by name. Some of them we'll talk about today, but the acrobat is certainly one we'll talk about today. Acrobat, not acrobat. Cart poles you've probably seen. But there's many actually. There's something called a penjubot. There's a Faruda pendulum. Reaction wheel pendulum is similar. Something called a convey crane system. I want to sort of list some of them just so if you do know if you've seen this work, you'll connect the dots. The ball and beam is another classic one. There's a hovercraft model people talk about. And then there's this, what used to be called planar VTOL, that nowadays we should just call it a quadrotor, because that's what everybody likes, quadrotors, okay? So these are all sort of classical systems. They're all similar in the sense that they are just a few degrees of freedom, typically 2 degrees of freedom for many of the examples. And they typically don't have enough actuators. So they're under-actuated in the trivial sense that you've got more degrees of freedom than you have actuators with which to control them. Okay, so yeah, there's a lot of great work, and one of the goals as we go through the different systems in the class is to understand what the world has done on these types of systems by showing some of the classic results from, let's say, nonlinear control for these systems and putting them in context. And then we're going to try to do, well, I don't want to say do better, but I guess that's what I mean. We're going to try to do better with sort of our algorithms, right? So we're going to see if we can have a generic solution that'll work for across the boards because we're using things like value iteration and the extensions that are required to make them work for more complicated systems. Okay, so today we're going to bite off a few of them, the acrobat and the cart pole, and then we won't actually spend too much time on the others because we'll try to They'll mostly follow. They'll just be different instances of similar problems. But the acrobat and cart pole are pretty representative. And then we'll play a little bit with quadrotors at the end, okay? Show you how it works. All right, so let's think about the acrobat first. The acrobat is a 2-link pendulum. It's an inertial pendulum now. It's not just a simple point mass model. So it's got theta 1 up here and theta 2 in the relative coordinates here. Okay, that's actually the way I've drawn it. That would be a negative theta. So theta 1 taking a negative value. Okay. It's got inertia in both of these links. It's got gravity pointing down, of course. What makes it special compared to sort of a canonical robotic arm is that we're going to give it a torque down here, and we're going to leave off the motor at the base. Okay? So just like it was actually Manolis who was just teaching in the room before us here. He's the one who made the joke before about if you had more research money, would you put more actuators on your robots? And no, we're going to leave that off for fun, not because we're poor. Okay, so the reason it's called maybe an acrobat is because it's sort of like an acrobat on a high bar, where you think that they do pretty amazing things, swinging around. They can swing up, they can balance, they can do flips, all the acrobatics, okay? But they don't really have much torque to give at the wrist. They're going to do most of the work they're doing by a torque down at the waist, okay? So that's, in that sense, you could think of it as a gymnast or an acrobat on a bar, but it's a robot, so we're going to call it acrobat. Okay, so the acrobat is going to fall neatly into our equations, our classical equations for the class, right? So we'll be able to write down the equations of motion with the manipulator equations. Okay, so in this case, Q is going to be just theta 1, theta 2. Okay, and B is going to be, it turns out it's going to be 0 and then 1. We don't have a direct control of theta 2 double dot, but we do have, we don't have direct control of theta 1 double dot, we do have direct control, so it's going to be 0 and 1 because U is just a scalar. Okay. Now H, C, and G can be derived very simply with the Lagrangian. I do it in the notes just for completeness, but these days you don't have to, right? So right, you can just count on them being implemented this semester by there's an Acrobat class, and there's a version that writes out the dynamics in H, C, and G form. If you want to think about it that way, there's also one that just pulls from the high-level robot description format. Okay, and what we're going to try to do with this is the classical problem for the Acrobat is to start from the bottom and swing up and balance at the top, right? Sort of surprising, actually, that when you're missing a motor at the shoulder, if you will, or at the wrist, if you're thinking of it as a gymnast, that you could actually balance it at the top, but it turns out you can. That's going to work just fine. There it goes, yeah. That's a randomly generated result. Normally it looks better, but what can you do? Okay, so, and if you want to see sort of the real thing, this is one that Ani did, your TA Ani. Let me see if I can get it to play from the start. Here we go. That's in lab. There's a little bit of a slop at the top that makes it hard to regulate perfectly, but it's perfectly, you can go up and knock it and it's balancing at the top. Yep, so that's in lab, right next to our couch and things like that. Okay. So the Acrobat's going to be the first system that we're going to see take to fruition here. We'll do right alongside that, we'll do the cart pole. Okay, so the cart pole system, some people call it the inverted pendulum, but since we just did a chapter on the inverted pendulum, I got to call this one something different, right? So this one is you might have guessed it, a cart with some wheels on it on the ground, and then it's got an inverted pendulum attached to it. Okay, and it could be a simple pendulum, that's okay, which has got a mass here. There's some mass of the cart. Okay, there's some length here. There's an angle of the pole, and there's an x position of the cart. And we're going to apply, the control input is going to be a force on the cart. So again, that's going to fit into our manipulator equations. This time we're going to use the degrees of freedom as the x position of the cart, and then the angle of the pendulum. Okay? And our control input u is going to be this external force on the cart. So B in this case is going to directly control the first degree of freedom and only indirectly control the second. In both cases, if we want to make it interesting, we can add a torque limit. Okay, so again, this one is a simple system to play with. All right, so if you just drop it from a random initial condition, you can see that this is that was passive, so the torque was 0, and you can see, of course, there's an inertial coupling between the moving pendulum and the cart, and we're going to exploit that in the other direction in order to move the cart in order to swing the pendulum. Okay, and our goal is to swing this one up 2 to the top. And then you have to not only regulate the angle of the pendulum, but you'd also like to get the cart back to 0. Okay? And if you want to see this one in real life, if you make it, you could also make this one a little more interesting by, if you actually implement it, you probably have a finite track that you've implemented your cart on, so you have to worry about the sort of hard limits in x as well as in u. Okay? But this is an example of the cart pole swinging up and balancing. This is Philip Reist's work. Okay, and this one is just, this video happens to be showing that it's a very robust policy that gets back very quickly from every initial condition. Yeah? Okay, so all right, so that gives you a sense. So now the question is, how are we going to go about building the controllers for these systems? These are canonical under-actuated systems. The rest of the ones, the Faruda pendulum, similar, you know, they're all of the same ilk, okay? So the first natural question is, does the dynamic programming algorithm we gave you last time work for this complexity? And the answer is, yeah, yes, kind of, right? So if you're willing to discretize the 4-dimensional state space now, right? Then, so let's see. So for my pendulum implementation that I showed you, we had 51 mesh points per dimension. And not to say I couldn't, I might have been able to get that down a little bit, but so if I went to do this on the cart pole with the same resolution, I've got 51 to the 4th mesh points. That means I've got, I don't know, 7 million or something, you know, 7 million mesh points. My transition matrix, although it's very, very sparse, is the square of that. It starts to be something that I don't really want to, it just doesn't feel like you should have to throw the book, like the power of distributed computation and the like at this canonical sort of simple under-actuated system. So we're gonna say that the DP solutions are viable just barely for this. And really, the best I've ever seen, I mean, because it's called the curse of dimensionality, right? That the amount you'd have to mesh goes up with to the power of the number of states, right? Really, the very highest power solutions you see out in the world are 4-state, 5-state systems. You really, you're not going to see people doing value iteration for more dimensions than that, and that's not going to suddenly get better thanks to Moore's law. There's an exponential here that we'd have to wait some time before we can do 6 states, right? So and then if you want to do a humanoid robot with 68 states, you're out of luck probably. Okay, so. So the discretized version of DP is, we're going to say, just borderline viable, but we're going to try to do better. We're going to try to find a more elegant solution. Now, we started last time talking about the continuous version of DP, and there's some hope there. We're going to extract some ideas there to get a pretty satisfying solution by the end of the lecture today for at least part of the problem here on the carpool and the acrobat. Okay, so there's a couple ideas that I want to pull out, right? So really the problem with this is that if we're discretizing based on these local function approximations, right? These sort of local cells that we've made some dense mesh over the state space, that's fundamentally going to break in high dimensions. That's just a no-go idea for high dimensions. You can't do that. So what can we do that's sort of a smarter representation over state for more complicated systems? Okay, so we talked about possibly using other basis functions. We're going to talk maybe a little bit more about that next week. But you could use polynomial basis functions or not. There's some limits into the guarantees you can get. There's a different idea that we can exploit here, which is trying to, instead of sort of making smarter basis functions directly, the first thing we can try to do is make approximations of the dynamics of the system, right? So maybe if we can say that, oh, well, in this regime, the system looks simpler, and I could use some very simple basis functions up here. Like if I'm close to the top, maybe I can say the system looks almost linear, right? And in the case of linear systems with quadratic costs, that was close to this case we did last time, we are going to have not only an efficient algorithm, but a closed form, so almost closed form, a closed form numerical expression for the dynamic programming solution at the top. Okay, and then the game after that is going to be, if I can do it sort of in the vicinity of the upright, can I do it in more places and sort of put together these smarter basis functions to fill the space? So I want to walk that path. I want to start walking that path with you today. So let's think about what it would take to linearize the dynamics around the top and how faithfully that will be able to capture the nonlinear dynamics. Okay? All right, so what the heck is Drake? And could you give us just a few minutes just to tell us what it is and this thing I'm downloading that's So I won't spend much time on it, but let me just quickly say a few words about that. So first of all, you should know that the code that you've downloaded is actually the same code that we run on Atlas. So that's kind of cool. And in fact, you've downloaded most of the control code that we field in the DARPA challenge. We haven't put all the interface and all the perception and all the other things in there, but we made a decision as a team that even though the competition's coming up still, we've been working really hard on the code. We might as well give it away and maybe have more impact that way. And certainly it's a cool tool for class. So first of all, you've downloaded the code for Atlas. I mean, there's simulations, there's examples for Atlas. If you're doing the precompiled distributions, I don't know if you've watched the distributions accumulate. I've been trying to build more and more of it on Windows, honestly. That's the big, you wouldn't believe how many hours I spend compiling. If you came in my office right now, you'll see, some books and academic and pencils and papers and then you see a build farm
on the corner with a Windows machine. Now there's a Windows 32-bit machine, there's a Windows 64-bit machine, there's a Mac, there's a Linux, and every different permutation of MATLAB license and everything. So we're working really hard to try to make it work on all your machines, just so you know. But the precompiled distributions are going to come basically with more and more functionality as they work on all the different machines. So the version you downloaded precompiled last week won't run all the Atlas demos. Atlas will just fall through the ground. But the one you'll download next week will be able to run all those demos. Okay, so if you want a quick high-level view of what Drake is, you can always look at, if you just go to the Drake website. The documentation is sort of always a work in progress, I guess, but it's compared to anything else I've ever written, it's actually fairly good. But so you can go to this Doxygen page and you can search for any of the methods and everything like this. But the thing you might not have realized when you're working with it and running a few examples is that it's really built to try to be, it's built in object-oriented MATLAB to try to be a way to provide some clarity to all of the structure that we have in dynamical systems. So it's all about nonlinear dynamical systems, and it's about exposing the structure in those systems so you can write algorithms that take advantage of those structures. So that's a theme in the class, and that's a theme in all of our work. And so for instance, there's this big class hierarchy that everything's a dynamical system, and then you'll see polynomial systems are, our affine systems are polynomial systems, our Drake systems, linear systems are examples like this. So there's this whole sort of class hierarchy of different systems, right? Linear is affine, is polynomial, is Drake. And there's some algorithms that we know how to write that we really know a lot of what to do with linear systems, and we know a little less about affine systems. There's some tools that work for polynomial systems that are very powerful. We're going to get into them in the next few days. And so basically by writing dynamical systems in this language, where you define basically the dynamics, the update, the output, and making sure that you expose the structure, then we've populated, you'll see in the polynomial system class, for instance, lots of different algorithms. Well, first there's sort of the standard thing that defines the class, and then there's lots of different algorithms that are built on top of that structure. The most important one in the polynomial systems is we know how to estimate regions of attraction for polynomial systems, and you're gonna learn about that next week. And if you look in different parts of the class hierarchy, you'll see, for instance, the manipulator systems. That's what we've been talking about now. So the manipulator, any manipulator is something that has this form, H plus C plus equals BU, right? And for those systems, we know lots of things. We know that it's control affine, and these are the algorithms implemented at the manipulator level are the ones that take advantage of that structure. Okay, so what you've downloaded is a big software package that tries to be clear about its thinking in dynamical systems and has lots of algorithms implemented for each level of those dynamical systems that we'll be exploring through the course of the class, and there's many that we've implemented in here that we won't get to in class. So you should feel free to poke around and play with it. Also, it's open source. You should feel free to contribute, and if you're excited about it, then as more and more people are using it, there's a chance it'll actually get bundled with MATLAB's robotics toolbox coming up. We're talking to MathWorks about that. So if you had an example that you like, or if you even have a final project you do for this class and you want to push it back into Drake, I'd be thrilled to do that. And we'll see how much use it gets in the long run. But for now, it's a tool that hopefully will get you to be able to run the algorithms we're talking about in class very efficiently on your own machine. You guys have experienced a little bit of startup cost and are running things like value iteration and stuff so far. But that's actually something we've never been able to do in class before, just distribute reliable code that lets you just run those examples. I mean, that took a lot of work. Okay, so maybe that gives you a sense of what Drake is. I mean, the biggest thing is that I think that's exciting about it is it really, it's not just for running toy examples for the class. We actually use it to run the robot. We run MATLAB on the Atlas computer while Atlas is running. A lot of people think that's crazy. I acknowledge that it's borderline crazy, but it's allowed us to do very fast implementations of some of these complex ideas and we really run Drake at 350 hertz on the robot when he's moving around. And the stuff that Scott showed you is real. It's actually running the same code you've got on your hard drive. Cool.
Okay, welcome everybody. Thank you for coming. It looked like you were all maybe finishing your homework a minute ago and just came in right at the buzzer, but that's okay. That's good. I have a feeling that the Mac update that automatically installed last night is what broke the Wacom, but who knows? So the Wacom's not calibrating today, so you get to experience the traditional approach here. So today we're going to talk, and I'm going to be on a leash. I've got one of those little dogs at home that every once in a while just runs and just at the end of the leash, you know. I bet I do that at least twice today. All right, so the topic for today is understanding what it means to be a locally optimal trajectory. Okay, and I hope by the end you'll have a good sense of what that means and the tools we have to understand optimality along a trajectory. But I've been listening to your feedback, and I want to take a few minutes before we start on sort of yet another topic to just talk a little bit about the big picture. Yeah, so I'm worried about this cable, but let's see. All right, so let's start with the big picture. Okay, so I've tried to convince you that there's lots of good reasons to think about your robot's dynamics. You know, if you have a balancing robot that doesn't have enough actuators, then it's required. But even if it's not required, there's lots of good problems, you know, if you wanted your robot to move fast at the limits of its actuators capabilities. There's lots of good reasons to think about the dynamics, right? We've seen a bunch of examples so far, but mostly in these sort of model systems. Acrobats and cart poles and stuff like that. And those are not so much the goal as the means to sort of get our head around the problems and the tools, right? Quadrotors might be the goal. They're fun. There's a lot of good reasons to work on quadrotors these days. But I want you to understand what I've been trying to do in the class, right, is I've been trying to talk about, we've talked about some of the classical approaches, right? Because that's what helps you understand, you know, the dynamics of the problem, the sort of the idea of energy shaping and partial feedback linearization. Right? I could have avoided those topics completely, but I think talking about them helps you really understand the problem domain and what a lot of people out there consider to be, you know, their favorite solution to the problem, right? But I don't want to confuse the message, although I think these are very important, and there's nice things that you can pull out of those topics, you know, some really nice computational ideas. Really what I've been trying to advocate, if you were to get a new system, if someone were to today drop on your lap a research problem, let's say I've got a robot that's got hard dynamics and I want to start controlling it, what I've been advocating in the class is sort of the optimization-based approaches. And for those are going to be my go-to tools. You know, if someone brings me a problem, then I'm going to go to these tools first. And I'll appreciate understanding and appreciating these tools better because I've gone through some of this this sort of literature. But really, this is the message I want you to take home. Okay, and even that message, I want to make sure it's not too complex, right? So there's been a lot of ideas kicking around, a couple different types of optimization. But really, the big picture is that I think for even your rich dynamical systems, your complex dynamical systems, very simple specifications of the problem using the language of optimization and optimal control can give you very rich behaviors, really. So for all of the systems we've talked about so far, it always was, every one of those systems, whether it was a balancing robot going to the top, or it'll be a quadrotor hovering, or even flying through a forest, we'll see, we're always somehow trying to get the system to a goal. And really in this, potentially you might think if we get this whole story about optimal control that the number of different objectives and formulations might be very diverse, but really every problem we've done so far, we've really only had two objective functions that we've talked about. We've talked about, minimize the distance to the goal in some quadratic sense. Or minimize the time to the goal. Right? There's sort of, so far, just two objective functions. Now, the solutions to the optimal control problem are diverse, right? So we saw cool sort of yin and yang kind of pictures of pendulums trying to get their, what their cost functions were as they were trying to swing up and get to the goal. And we saw switching surface for double integrators, and the pictures for the acrobat and carpal are higher dimensional, harder to plot, but they would be even more rich, right? But the richness in the solution comes from the dynamics and the constraints. But the objective functions really are very simple. So far the story has been, you give me a new robot, if it's a type of robot that's just trying to get to a goal, I'm going to formulate an optimal control problem, depending on if I want to get there maybe with less effort. A lot of times I should have put an effort in here, right? And maybe this one typically is only well defined with some limits, right? But there's really only two messages, two different choices we've talked about so far. Okay, all that other richness is coming from the dynamics and the constraints. All right, and the solution to these optimal control problems has been a feedback controller, right? The optimal one we've been using always star. Okay, and we'll get variations. We might have the time-dependent feedback controller or whatever, but it's actually been a pretty simple story so far, intentionally. Okay, and then the diversity in the different lectures so far has been how do we actually solve from the specification the optimal control problem, right? And we've had a few different. So, Ani, do you prefer me to stay here or?
Yeah, if you don't mind.
Okay, yeah. Right, and then the solution techniques for small problems, right? We could get away with discretization or some limited function approximation and do basically graph-based dynamic programming, right? Sort of brute force dynamic programming. And for bigger problems, we've had to do some approximate solutions, right? And so far it's been approximate versions of this DP algorithm, right? So, you know, one thing we talked about is, for instance, linearization plus LQR. Okay, that's been the big one so far. And then there was this new tool that the problem is there's a gap between dynamic programming and sort of approximate DP. If I'm going to make some approximations when I solve my optimal control problem, then you're left with something that you don't really know when or how well it works. So the last lectures on Lyapunov were to combat the fact that we're making an approximation here. We're giving us tools to verify the approximately optimal, you know, the approximation on the original system. Right? And so one very tangible way that we said that could pay off is if we're thinking about you know, some complex, very nonlinear dynamics that we're approximating with a linear system, and we do an LQR controller. See, I didn't bring my colored chalk. That's the limitation here. I bring my linearization in here, and I do a linear controller. Then I could use these Lyapunov techniques, for instance, to say I can rigorously estimate an inner approximation of the region of attraction, so I know that my linear controller is going to stabilize the system as long as it's inside this region, right? Okay, but this is just building up your set of tools to solve this big problem, which is to try to solve for the optimal controller to the best, or some approximation, you know, to the best we can for potentially really complicated systems. Okay. So the details of the Lyapunov, there's beautiful details there. I gave you sort of a 2-lecture introduction to it, and the sums of squares optimization on top of Lyapunov is a diverse topic that we spend a lot of time in the research lab thinking about. There's lots to learn there if you care, but I really want to make sure that you see that in the bigger picture, that's a set of tools which complement the fact that we have to make approximations here. We can come back and verify exactly on the original system our approximate controller. Okay, that's the role they play, and we're going to use them to potentially build better controllers by building provably good controllers in lots of different regions. Yes?
When you're doing the like STP, searching over the Lyapunov function like Rational multiplier, what do you use as your objective function? Because you're trying to find something to maximize kind of the size of the region of attraction. So I kind of missed that in the lecture, maybe, or if you don't want to talk about it here.
I'll give you a quick answer here, and I'll talk about it as long as you want afterwards. But typically, the metric is to somehow maximize the volume of the region of attraction. And for complicated regions of attraction described by high-degree polynomials, estimating that volume is very hard. But typically we'll do, in the actual code, estimating the volume of an ellipse is easy. So we'll do somehow a contained ellipse and push out on the biggest possible contained ellipse that isn't completely inside this. And that's our surrogate for volume of the region of attraction. And it's decent. It seems decent. But this is a great time. If anybody has questions about sort of, what the heck all these different topics, how they fit together, ask away. Yes?
So comparing LQR to hole placement methods I've used in the past, it seems with hole placement I have a lot more guarantees that what I make is going to be stable, and with LQR there's a lot of guessing at what the gains are. LQR equivalent to see how far your poles are in that imaginary axis?
You can always, of course, pull out the poles of the closed loop system that you get from LQR, but I think the bigger difference you're sensing is that you're applying a linear controller to a nonlinear system.
Yeah, okay, that's better.
So if you had done pole placement on the nonlinear system, you'd feel the same pain.
Okay.
And because LQR applied to a linear system, for any positive Q and R, is going to give you stable poles.
Okay.
And the question is, when you apply that to a nonlinear system, what do you get? And that's where you start getting into the maybe the art of picking Q and R. In my experience, it's easier to pick Q and R than to move poles around, but maybe that's just the way I grew up, that I thought I'd like those tools better. If I had done pole placement first, then, Good, okay. Right, so, for small problems in DP, that's like state dimension, less than 4 or something like this. LQR basically will work for all intents and purposes for arbitrarily complex systems. You end up just solving a few matrix equations, and those can be very big these days. For robotics, very big. That's good. And then sort of scaling wise, these Lyapunov tools can solve a lot bigger problems than the grid-based dynamic programming, but not as big as LQR. So we don't run this on the full Atlas model, for instance, but we're certainly able to run it on quadrotors and things of that complexity in the maybe tens of dimensions, 10 dimensions or something like that.
How robust are what if you're using your nonlinear model, that's even an approximation, so how robust is the controller and your estimate of the region of attraction, given that you have a model errors there?
I think you're referring to the fact that we do Taylor approximations in here to make it a polynomial system. That's a choice that we made for various reasons, but partly for simplicity to show you what we do all the time. It's not strictly required. Most of our systems are actually polynomial, but they tend to be higher degree polynomials and might be numerically more difficult. But you can actually turn a rigid body system into an exact polynomial. The approximation is not fundamental. And even if you did do a Taylor approximation, you could bound the errors in the Taylor approximation and you do robust verification to capture those errors. So I think those gaps can be addressed pretty nicely. Okay, so we've got something that scales really well, something that's local, right? It's limited to the linearization region, but scales very well, okay? And then something sort of in between that for the systems we care about, this is going to be, I think, a sweet spot for us where, you can think about maybe 10 dimensions or so, and that's going to be pretty darn good for the kind of problems we care about. But still, I've only really given you, a somewhat satisfying answer around here, and we haven't talked about, what happens in the rest of the state space. I gave you examples of energy shaping and partial feedback linearization to get up there to understand a non-optimization, but a sort of physics-based view of how do you design a controller. But I haven't given you yet an optimization-based approach that scales, that's going to work beyond sort of the linearization region. And that's the goal for today, okay, is to try to understand what you could do out here. All right? And really the fundamental problem is as the dimension gets higher, and these nonlinear systems are potentially arbitrarily complex. The solutions might be very, very complex. You just can't look at everything. There's somehow you have to give something up in order to come up with a technique that scales to high dimensions, okay? So the thing we're going to try to give up today is we're going to give up, what we've been solving for so far is trying to solve the optimal controller from every possible initial condition. And the approximation I'd like to do today is let's restrict our attention to trying to find an optimal controller from a single initial condition. You pick the initial condition, you pick any initial condition. I'd like to come up with an optimal thing to do from this initial condition, okay? And then, I'm going to be able to think about sort of a solution trajectory that gets me to the goal, let's say. But it's something that is sort of natively one-dimensional, even if I'm applying it to a very high-dimensional system, right? So somehow this is going to scale But solving for every possible system initial condition in a high-dimensional space is not going to scale, right? So let me draw that. Let me try to capture some of the subtlety of that. Because that's a big thing to give up, right?
Just in case I forget to say it in the middle, so we're going to be using a new set of tools, of optimization tools for the materials we're covering today that you'll use on your problem set. And there's instructions in the problem set to help you with this deal. But there's a one extra solver that you'll need to install to use along with the MATLAB solvers. MATLAB's going to call a solver that can handle the types of problems we generate, the convex optimization problems we generate based on the material today. So you get your pick. You can install, if you love open source, then you can install Sadumi, and it's free to the world and everything, but it's a little slow. And if you want to, if you don't mind installing the commercial solver and using the free academic license, it'll be faster and numerically a little better. So you have a moral decision to make. I installed Mosaic personally, which is the commercial one. Okay, so last time I tried to give you the background we needed to talk today about one of the topics that I'm actually most excited about that we pursue very actively in the research group right now, which is using optimization to do the Lyapunov analysis that we talked about last time. And I hope to convince you, partly today, but over the next few lectures too, that it's about more than producing proofs that a system is stable, but it'll actually help you in the control design process. So today is about Lyapunov analysis using sums of squares optimization. And so it's a bit of a tall order here to tell you all the pieces that we need to make you understand this story completely. So I'm going to do my best to give you the background only to the extent necessary to give you to understand the big idea here today. So we need to know a little bit more about optimization first. So we've seen optimization a few times in the class. It'll be a constant theme. A few examples that we've seen already, just to make sure it's all tying together. When we talked about the dynamic programming discrete update, we wrote down equations that said for every S, I'd like to make some update, which is minimizing over A, right? GSA. The equation's not some. This is just to jog your memory here of SA, where this was the state transitions. This was my cost to go, right? But in the middle, we started using the language of optimization, right? We used this minimization in the middle, and in the discrete case, that meant literally you could write an algorithm that tries every A and take the minimum value. Right, so that was sort of easy to program. Right, I try every possible A, because this was only looking over A's in some discrete set of transitions in my graph. And I plug it into this equation, I get a value out. Whichever one is the smallest value I'm going to keep, and that's the output of my minimization. That's sort of trivial, discrete optimization. We've seen a couple examples in a continuous domain where we used the same language, right? We said min over u, and in the special case where we had some quadratic cost plus some f2u, if we had something that was quadratic only in u plus some other stuff, then in that case we said, okay, we can solve this minimization problem in closed form, because this thing, since I knew r was positive, then I know this thing is just going to look like some sort of quadratic bowl wherever it is. So if I look at different values of u, I know that it's going to be some simple thing like this, So I could actually find the minimum by looking at the place where the gradient with respect to u was 0 and finding that point. That was another instance where, another extreme where this was a continuous optimization, but we were able to solve it in closed form by just making a gradient argument, right? Now today we're gonna broach sort of the more complex forms of this optimization. So this already gets more complicated if I were to put some sort of constraints on u. Let's say if I added some bounds on u or other things, then this simple analytical solution doesn't work anymore, right? In general, right? So the general sort of nonlinear optimization is hard. It's a hard problem. So, right, if I were to, in general, use the language, I'm going to minimize over some decision variables alpha, some objective. Let me write that as just some big function of alpha. Right? In general, if I don't have knowledge of what f is, that could be a really hard problem. If I plot alpha, I could have some complicated function f of alpha, and there might be not much I can do, certainly in closed form or even with a computer, to find sort of the global minima of this without short of brute force searching. It might be very, very hard. So if I write this down in general, it could be hard. I mean, our goal would be to find some alpha star, but it might be that we find some local solution, which I didn't give myself a very obvious local minima here, but it might be that I get stuck with something here if I'm just trying to look at gradients or something like this. I might get a very bad solution. It's hard to solve this problem in general. Okay, and the full-blown nonlinear optimization also allows you to encode extra constraints on alpha. I could say subject to some list of inequality constraints, G, that can be a vector G, right? Just so you have the language, this is a scalar objective function, right? This is my objective. These are my constraints. And these are my decision variables, right? Okay, so in general, optimization's hard. All right, so today we're going to talk about something that's maybe halfway between this general nonlinear optimization and the closed form solution. It's a problem that's hard enough that I have to ask the computer to solve it for me and just settle for a numerical solution instead of an analytical solution. But it's actually much easier than the full-blown nonlinear optimization problem, in the sense that there's a class of problems where if I ask the computer, I'm confident that it can efficiently find the global solution, right? So you can imagine that if f took a particular form, if f was some sort of easier function, in fact it's going to be a convex function, then I'm going to be able to rely on my computer to find the best solution efficiently. And similarly, if these constraints form a convex set, then I'm going to be in the world of convex optimization instead of nonlinear optimization. And it'll be surprising, it's been surprising to me how many problems can be formulated as convex optimization problems. And they have very efficient solvers available, which you'll download, either free or commercial. And they're going to be able to solve these problems for us almost to the extent where we could think of it as it being a closed form solution. Okay? So how many people know convex optimization? Feel like they've seen that before? Okay, that's about what I expected. That's good. All right, so let's just tell you a little bit specifically what I mean by convex optimization. So now this is a rich topic. You could take a whole semester course on it. I feel like I say this every lecture. It's really annoying. It's a rich topic. You can take a whole course on it. I'm gonna spend 5 minutes on it here, but I think you're gonna have enough to be able to be extremely effective with the tools. Okay. Oh, I'm sorry. Yeah.
So when you're performing this, how do you know your value functions on the right hand side? So you have to know something about the convexity of that a priori to actually use this method. Like,
So I wanted to put that in context with the value function we did before. You're going to see immediate application today with the Lyapunov instead of the value function, and it'll be crystal clear in a few minutes. Yeah. So how would you use that in the value iteration loop? We have an answer for that too, but it's a slightly harder story. Okay. So what does it mean to be a convex function? I think you know intuitively what it means, right? So a function is convex in its parameters if it's shaped up, if it's sort of pointing upwards like that, right? So what's the technical definition, right? So if I take any 2 points, let's call it alpha 1 and alpha 2, and I look at the function evaluated at those 2 points, then I should be able to draw a straight line between them that is everywhere above or equal to the function. That's how we're going to define a convex function. Okay. I can write that mathematically very simply. This line segment here is defined as a affine combination of those 2 points. So if I make a number beta that goes from 0 to 1, and when beta is 0, I'm over here, and beta is 1, I'm over here, I could write that as beta alpha 1 plus 1 minus beta, let's say alpha 2. That would walk the line between here and here, right? That would parameterize this line segment down here, right? And what I care about, I should use my colors. What I care about is what's the function over that interval. Okay, so I would like that some linear combination of these points, which is going to be, let's say, beta f of alpha 1 plus 1 minus beta of f of alpha 2. Right? That's my combination of this. That had better be greater than or equal to the function evaluated at the point in between. So okay, that's just saying exactly what I said in pictures, that this line, the combination, and this is always for that, yeah, this line is everywhere above the function. Very simple definition, simple test. So our objectives in convex optimization should be a convex function. The other thing we need to understand is our constraints have to be a convex set. Okay, so intuitively what a convex set is if I have some region of possible parameters, let's say it's in alpha 1 and alpha 2, right? And I say any of these are okay. Then what that should mean, the definition of a convex set is if I pick any 2 points inside that set, then the line connecting them should also be inside that set. The line segment connecting them. Yeah. So exactly analogous, right? So if alpha 1 and alpha 2 are in some set, call it G, I guess, then beta times alpha 1 is 1 minus beta. 2 had better be in G. Okay, so my objective, you can imagine that if my objective is like this, it should be easy to find the minima. What the function being convex implies basically that there are no
spurious local minima. There's no place to get stuck if I'm doing optimization. Yeah? And the set being convex is important for that too, because you could imagine, let's give an example of a not a convex set, right? If I had some set like this, right? And this not convex, right? Then you can imagine getting a solver getting stuck if I've got some, even if I've got a smooth objective function and I'm trying to get down, then maybe I have to, maybe the minimum is over here, but I'm stuck here thinking I can't go any farther, if that makes sense. If I were to be looking at the objective along this line, it might look, even if the objective is smooth, there might be a gap in what I'm allowed that prevents me from ever looking and finding my path down to the real minima. So you need both in order to have an easy optimization problem. Does that make sense? We started talking last time about walking, and there were a couple of specific things that came in with walking that we hadn't talked about before, the idea of stable oscillations and the ideas of impacts. Those are going to be, especially the ideas of impact are going to be general if we want to start talking about manipulation and other topics in nonlinear control for robots. These are going to be ideas that transcend walking, but walking has some really nice simple models that you can get our head around and think a lot about. So today I want to take what we did last time, the basic sort of understanding of the dynamics that we got last time, and try to start looking at the same dynamics but with the lens of computational algorithms. Okay, so last time you'll remember we talked a lot about the rimless wheel. Right, which was our toy model of a wheel on a slope, gamma, of a simple pendulum, basically. A point mass with some spokes coming out of it. Okay, that was rolling down the hill. And one of the remarkable things about that system was that even though it was completely passive, it quickly fell into one of two stable solutions. One of them was standing still, and the other one was stable periodic motion. Even if it was started very quickly, it would slow down and it would always roll at the same speed, right? And the way that looked, you remember, because this was a pendulum, we could draw it. We moved the coordinates on us just because I wrote it on the upright, but we still have the homoclinic orbits we're familiar with. It's just now centered around the origin. We had a couple of big important places in state space here, which is when one of the feet came around and hit the ground. Importantly, it's asymmetric, right? So this one was at gamma plus alpha, and this one was at gamma minus alpha, where alpha was the half of the inner leg angle. And we found that the solutions to the system here were familiar. The stable limit cycle was an oscillation that looked like this, slammed its foot into the ground, and then had a reset map that brought it back to this, because we just rewrote the coordinate system around the new stance foot, and we had a stable oscillation like that. Okay? So this was the one system, the one walking system where we could completely solved in closed form, right? For instance, one of the things we talked about was the ability to analyze the stability of a limit cycle by analyzing the stability of the Poincare map. Which was an n-1 dimensional map. Right? So whatever our state space was, it was one lower dimensional map, which went from
sort of the reduced dimensions, I'm calling it x Poincare, xp at time n, at crossing n to crossing n plus 1. Right? This is a discrete map that, for instance, would go from the time one of the foot left the ground all the way back to the next time when the foot was leaving the ground. Okay? We could have taken it around some other point as long as all of the trajectories transverse through that Poincare map, then I can extend some of the stability properties of this map to the stability properties of the original system. That's a big time idea. Because what it did was it allowed me to do fixed point analysis on the map. Told me about limit cycle stability of the original system. Does that make sense? Maybe surprising that you can make that sort of, you can lift up and make a statement about the higher dimensional system, but I think hopefully the machinery makes sense. There's a snag though. If we start to go to implement this for more complicated systems and try to sort of use our Poincare map in order to infer something about the more complicated systems, the snag is that we'll almost never be able to write down P in closed form, right? In general, getting the solution of the system from going from one crossing of a surface of section to the next means integrating the equations of motion along some solution, and that's something that we typically can't do, right? We could only do it here because it was a passive system. We used conservation of energy, and it was trivial to do that. But in general, we can't do that. Okay, so what do you do if you can't write down P? Well, there's simple things like you can do numerical integration, and you can estimate P by running lots of simulations, even doing our sort of sensitivity analysis that we did for computing gradients of trajectory optimization. There's ways to sort of work with numerical versions of P. But I'm going to advocate a slight generalization on Poincare maps that's going to make everything work a little bit better today. Okay, and so, yeah, so the goal for today is to sort of generalize these tools to things that are going to work better with our computational objects. All right, so in fact, what we've done so far, our major tools so far have been well, let's say LQR feedback, then we did some Lyapunov analysis, and we did trajectory optimization. And in fact, you're going to be able to do all of those for these systems that have limit cycles and impacts as well. Just for fun, let's go through them in the opposite order. We'll mix it up. Okay? All right, so let's think about trajectory optimization for this sort of walking system. And let me ask even sort of a simpler question, which is, so the rimless wheel doesn't have any control inputs, so maybe trajectory optimization isn't, designing a control input isn't so interesting for that. But there's even a sort of a fundamental question you could ask. How would I find, let's say I had a more complicated system, how would I even find a stable limit cycle or a limit cycle that exists? How would I find a periodic solution? right? So if it's as stable as the rimless wheel, you could just start simulating and hope that it falls into into the limit cycle you're looking for. But our goal as control designers is to do things like stabilize the unstable systems, right? So that's not going to necessarily work, right? In general, we might want to find a periodic system that requires some non-zero control input in order to make it a periodic solution, right? How can we find that? Turns out you can formulate this problem and many more with the tools from trajectory optimization. And I hope this doesn't surprise you, but maybe it's a reminder of just how general and potentially powerful the tools we've already started to show you are for thinking about dynamical systems. Okay, so if you think about our rimless wheel example specifically, let me zoom in just a little bit on the phase portrait. Okay, there's a couple things going around here. A couple things at play. We have our equations of motion, which we know were just ml squared theta double dot. It's minus mgl sine theta because we flipped it upside down. Okay, so we have our equations of motion. We have our discrete reset map, which we figured out turned out to be simple just by conservation of angular momentum. It turned out to be that the velocity just after an impact, which I was writing as theta dot plus, or maybe, yeah, that's fine, just turned out to be a simple function of the velocity pre-impact. Okay, so we can do trajectory optimization on this. If you think about what it takes, let's do one of the direct methods. We could do a direct collocation or a direct transcription. But my state space here, of course, is just theta and theta dot. You can imagine listing out decision parameters. Let's just list out the state. We don't have any control here. I could do x0 to x big N. Okay, and let's just start leveling the constraints against the problem, right? So I want to find some solution that has, well, let's say my initial condition should be somewhere. I don't know exactly where it's going to be. I want to find whatever the right periodic cycle is, okay? But it's going to be somewhere along this line, let's say. I could say that theta at time 0 had better be somewhere on this switching surface. I could say that theta at time n had better be on this switching surface. Okay, I could say that that my update map had better hold. Wherever I end up on the end here had better be a reset map away from this, right? It must be that theta dot at 0 had better equal cosine 2 alpha theta dot at n. Okay. Of course, I need my dynamics to hold. I need my x at n plus 1 had better equal f of x at n. Can you think of anything else we need? Yeah.
Quick question. So we're constraining the initial theta and the final theta,
Yep.
and then we have our update map. Isn't there a problem if we have like a fixed time step?
Okay, good question. Right. So what happens if my time step didn't quite match exactly this? Yeah. No, you're right. Absolutely right. So I didn't even think to say that because our formulations eat these dynamics and allow dt to be a decision variable also. But you're right. I should put in the time step as a decision variable. Good call. What else? Is there anything else you need to say? It's exactly that kind of thinking. What else would we have to throw in here? To be a solution of interest, it better be, I mean, if you think about this, all I'm saying right now is I'm telling the program to throw down a bunch of points, and then it's going to have to pull them into something that's dynamically consistent. It's going to pull one of those points here, one of those points here, but I haven't actually told it that any point that hits here gets reset, right? I haven't sort of told it all the rules of the game yet. So in order to be valid, I better also say that all of those intermediate points are not actually at the switching surface. Yeah? So let's say that for all I, let's say for I 1 to n minus 1, theta I had better be less than this. And similarly, I could say that 2 to n theta I had better be greater than the other side. I don't really need that nth one or the first one because those are already constrained. But okay, so this is just exactly a trajectory optimization problem we've already seen, but I'm just giving it a few extra constraints. One is that it starts and ends at a particular part in state space, but I'm only constraining the position, not the velocity. Okay, and the second is that this rule here, this update rule, gets enforced, and that's going to constrain that it's going to be a periodic solution. And then I can just go and ask the optimizer to try to figure out, find any solution to this. I could put in an objective, but it happens that we know there's only a unique solution for this particular problem, so I don't actually need an objective. If I can just find any solution to that, that satisfies those constraints, I should have found my limit cycle.
So it's okay that there's going to be probably a unique solution to that, like we saw, like the optimizer can still find it if it's like a general like that.
If it's what?
If it's like you're telling it to search over a constraint set that's like.
My objective is 0, and so if it can find any solution to this, it'll be happy.
I know, but like your solution set is that particular limit cycle that we're looking for. That's like a 0 dimension, like a lower dimensional space. The optimizers can still do that.
Yep. Yeah. I mean that's always true of constrained systems, right? Of constrained optimization. Yeah. Okay. So I mean, I did exactly what we just said. I said theta 1 is gamma minus alpha. Theta n is gamma plus alpha. Theta 1 dot this is my periodicity constraint. I said let's keep the theta in the range for all the intermediate points. I have one extra state just because for my animation, just to make it look cooler, I actually keep track of how far it is down the ramp. I said the initial condition 0 for that. Almost all this code is just to plot it pretty for you. So like line 25 to 50 is just to make it a pretty plot for you guys. 51, look at that. And then I solved, right? Okay, here we go. I forgot I rebooted my machine, so I gotta wait for Simulink to load. Okay, it's a trivial problem for the optimization. Can you guys see that well enough? I can't. I just plotted that those red distracting things are just the vector field, just for sanity. The green is my homoclinic orbit here. This is just some constant energy orbits, just for reference. And it really does happen in. I mean, this is sort of an easy problem for the solvers. If I plot every iteration of the algorithm, you're going to see there's a few of them that are off the screen. It converges basically in 3 or 4 steps. Okay, boom, finds the limit cycle. Yeah, it understands the dynamics, right, in some way. It's got the reset. It's found our periodic solution. Okay, now that's a recipe that we're going to have to generalize it a little bit just in the way that I wrote down the constraints. But that's a recipe that's going to be able to work for very complicated systems, potentially. Okay? Does that make sense? Yeah? All right, so let's generalize it a little bit to make it work for something that's not just, always at gamma minus alpha to gamma plus alpha, right? There's a slightly more general picture you need to have in your head when we talk about systems with impacts like this. Let's just take a second to figure out where we are in the class, right? So we've been talking about acrobats, cart poles, quadrotors, and the like. And I've given you the basic recipe, right? So a basic recipe, computational recipe for dealing with systems of that ilk, right? That are sort of potentially complicated rigid body systems, but so far they've been smooth. They haven't been colliding with the world. They haven't been avoiding obstacles necessarily. But if you have sort of balancing robots that you'd like to control, then doing LQR at a fixed point works very well, right? Doing Lyapunov analysis to figure out where that linear controller works for the nonlinear system works pretty well. Trajectory optimization, I hope you left with the problem set with the impression that that actually works pretty well. And you're not supposed to laugh. That was not a joke. And then stabilizing trajectories with time-varying LQR. That works very well. That's a recipe that I think will work well for you in a lot of problems. There's lots and lots of variations for all of those steps. I covered just the basic formulation of trajectory optimization. I put at least call-outs to more of the formulations in the notes. There's lots and lots of variations and extensions. Same thing with the LQR. There's lots of variations. I put a lot of them in the notes too. For instance, if you want to absolutely guarantee that you get to the goal at the end of time, there's a way to formulate the LQR problem that does that. All kinds of variations. Okay, so we've given you a basic recipe that's going to work for a lot of problems, but there's lots of things it can't do. So for instance, we haven't given you tools that are going to always find a trajectory if one exists, right? So let's say I have a quadrotor and I want to fly through a forest, and I start doing trajectory optimization. I say I put a final constraint saying I need to get to this goal in the forest. There's a good chance that the trajectory optimization tools we've given you will try and will fail and just say I can't find a solution. We haven't given you guarantees that that algorithm is going to find a solution if it exists. We will give you tools that'll have that guarantee soon, but just understand we haven't given that to you yet, right? And really what we've given you in terms of the trajectory optimization is a local solution. It's something that's going to take an initial condition of interest and maybe some small vicinity, because we're going to stabilize that with LQR, that's going to give you a controller that works from a small set of initial conditions. We haven't yet given you a tool that's going to work from many, many initial conditions. We'll try to give you those tools soon, but we haven't yet. Before we dive into making those tools more sort of address those more complicated problems, I want to play with our basic tools a little bit more on a variety of different systems. Okay, so today is about seeing what it takes to take the stabilization, trajectory optimization, and other tools and understand how they work with something that's just a little bit harder than what we've done so far. We're going to take our balancing robot and turn it into a walking robot. Okay, and the basic details that come in are, for instance, having a hard discontinuous impact with the ground. That's an event. It's a discontinuity in our continuous solutions, and we have to deal with it explicitly. There's another thing that we're going to talk about today, which is the idea that I don't want to necessarily stabilize a point in state space, but potentially a periodic solution of state space. So we're going to talk about limit cycles and limit cycle stability today. Okay? And really today I'm going to talk about the dynamics of walking. And on Thursday, we'll talk about how you start bringing those numerical methods to bear on those dynamics. Okay, so let's start talking about walking robots. One of my favorites. Okay, so it turns out, so I've already motivated this by showing you videos of Asimo and videos of passive walkers and told you there's a number of different approaches out there. Some of them rely on the dynamics more heavily. Let me just discuss for a minute here there's this general feeling that walking is still an unsolved problem in the world, right? So compared to a robotic arm on an assembly room floor, which can do exquisitely impressive behaviors at rates far exceeding a human over and over again, our walking robots fall down a lot. They use 20 times more energy than humans when we walk, and they're generally considered not where they should be in the world. Things have come a long way in the last just few years, but there's something still fundamental about what we can't do with walking robots, right? All right, so what makes walking so hard, right? I'll give you a short list here. Right. First of all, walking robots are just inherently complex, right? You end up with robots that have many degrees of freedom, many links, right? So you just end up with complexity from that. I honestly don't think that's not a big problem. That's an okay problem, but that's a practical problem that if you end up building a walking robot, you got wires running everywhere, you got just hardware issues, right? Compared to a quad rotor, those things just work pretty easily, right? There is a problem that goes along with that, which is that you do have to carry your actuators. So to some extent, there's a fundamental interchange between having actuators that are powerful enough to do everything you need to do versus the size of the actuator you have to carry, right? So Songbei actually addressed that beautifully today. He talked about his actuator selection strategy for Cheetah and designed some custom actuators that gave instantaneous torques that were sufficient for his running experiments, but it required a custom actuator. But what it means is, oftentimes we're dealing with input saturations or power limits sort of beyond what you might have to do if you were a robotic arm that had a tether to the wall, right? There's been a few dramatic exceptions to that rule. So for instance, Boston Dynamics has been building robots based on hydraulic power with a gasoline engine attached. And gasoline is basically unlimited power. So if you're willing to go there, then you can get around some of the fundamental limitations. But the electric humanoids have traditionally suffered from not being able to move their legs as fast as you'd like to, right? So the big difference is if I get pushed and I have hydraulic power, then I basically can put my leg back as fast as I need to catch myself. That makes stabilization relatively easy. If I'm a humanoid robot relying on a geared electric motor and batteries, and I get pushed, then it's somehow I have to be smarter about getting my leg back because I can't just move it back arbitrarily fast. Okay, so actuator limits are absolutely real. Okay, I can't believe this is my third one, not my first one. Systems are under-actuated, right? Right. So fundamentally, where a robotic arm is bolted to a table, a walking robot is not bolted to the table. It has degrees of freedom. It by definition has more degrees of freedom than it has actuators. Right. It's not because I don't have enough funding. It's because fundamentally, if I'm not bolted to the ground, I have extra degrees of freedom. If I put an actuator between my foot and the ground, I'm not going to walk very far, right? Okay, so these things, I think, we've already developed some tools to deal with. Okay, there's other things that we haven't dealt with yet, right? So I think the complication that comes with impacting the ground. That's a new sort of complexity that we're going to deal with today. The other one I said is that often the goal is periodic behavior. So we're going to start talking about limit cycle stability. So these two are sort of the goals for today. So start addressing those. And then there's some other really, in practice, sort of very important practical problems, right? So it's, these robots are just fundamentally difficult to model. Unlike some of their, like a wheeled robot or certainly a factory room robot, they depend on their interaction with the ground, for instance. And so you either need to perceive the ground at with high quality perception, estimate the friction properties of the ground you're about to walk on, right? It's fundamentally, there's just a lot of uncertainty out there, and it's hard to have good models, right? Even if your robot internally, sure, you can get a good model, but it's hard to know, if I step on that rock, is it going to teeter and fall, or is it going to stay, right? It's fundamentally hard to know the dynamics of your robot. And a walking robot depends so heavily on its interactions with the environment that makes it very hard. And going along with that, not having the model, there's no global reference frame for a walking robot. So there's a premium on state estimation. And I'd say as a community, we're still getting our head around the state estimation problem for walking. But there's been good local work on that. Okay, so we're not going to get to those today, but we'll at least give we'll talk about them a bit towards later in the class.
Okay, today we're going to talk about trajectory optimization. Let's remember our motivation. Okay, so our goal, we've been formulating a number of times in class, the idea that we could do control design as an optimization using optimal control. Right, so the goal in optimal control is to somehow solve for every possible initial condition. I'd like to find some controller which minimizes an objective function, right? So we've been writing it often as in some additive cost, infinite horizon objective function, right? Subject to, for instance, making sure that the dynamics are satisfied and that my initial conditions are at this. This is one way to write down sort of the optimal control problem. And maybe I have some additional constraints. Like input limits or state constraints, right? But this is hard. Solving this problem is hard. In particular, it scales poorly with dimension, right? Right, if I have to check, if I have to solve for every possible x0, where x0 lives in some high dimensional space, then that becomes computationally extremely hard to do. So the idea we started talking about last time was instead to solve for a single x0. Maybe the state that I'm in right this moment, and we're going to give up on global optimality and just worry about having something that's what we call locally optimal, right? Right? The reason we have to do that is because the only way to accomplish sort of global optimality is still to look at every possible state, because there could always be some path, behind the rock over there, maybe around the tree in a way I didn't expect that could be better than the one I'm thinking about right now. So if I have to be guarantee global optimality, then there's really, again, no way to avoid examining every possible state of the system. So in order to somehow scale to higher dimensions, I have to focus on a particular initial condition and be willing to accept only local optimality. We talked about, so the global optimality was related to the sufficient conditions for optimality, right, which we got from the Hamilton-Jacobi-Bellman equation before. The local optimality, right, we can still give necessary conditions for optimality, right? So being locally optimal is still, of course, necessary to be global optimal, but it's just not sufficient, right? And these are the tools that we learned last time associated with Pontryagin's minimum principle, right? And just to remind you what it means to be locally optimal, right? So if I have some solution trajectory x star u star that I have as a candidate for local optimality, local optimality means if I change either x or u by some epsilon, then, well, either my cost goes up or a constraint is violated. Right? So one of the others has to happen, and if I could say that no matter how I change x and u here, I always get worse in some way, then that's my definition that in this x and u I'm locally optimal. And again, it's a necessary condition for optimality, but not a sufficient condition. The trick is this necessary condition for optimality can be checked in high dimensions, and what's more, we can actually find locally optimal solutions in high dimensions. So we're going to get algorithms today that scale well to high-dimensional complicated robot problems. Okay? The reason it can break that cursive dimensionality is that I can write down x and u parameterized not in the dimension of the system, but parameterized only by time. Right? So I can get a sort of a one-dimensional signal here, meaning, well, it depends only on time, that describes x and u. Okay, so that class of algorithms, the numerical algorithms associated with finding locally optimal trajectories, is called trajectory optimization. Let's see how it works. Okay. So the first step to make it an algorithm, right, is to come up with some sort of finite parameterization of those trajectories that we're searching for. Right, so if I write down, I'm going to try to find some u star of t, but I don't know how to search over continuous functions with the computer with finite precision, finite memory, right? So I need to somehow come up with a way to parameterize that. And there's a number of classical choices, and they're all easy, right? But so if I want to come up with some parameters that maybe I describe the value of ut at a handful of points, right? And I can call these my parameters, maybe u0, u1, u2, u3, u4, right? u5. Then these parameters here, there's a finite number of them, and they can describe the continuous function u of t if I make some decisions. So there's a couple of decisions I could make, right? I could just say that the value in between these is just whatever it was. I'm just going to hold my previous value until the next value occurs. This is that would be the piecewise constant. Or zero order hold, also known as zero order hold approach, right? Another totally reasonable approach would be to say that the function is piecewise linear between these points, right? That would be the first order hold. Or another very common approach would be to have a smooth function that goes through these points, which the standard solution would be to, if you had a piecewise cubic. Which is often called the cubic spline. And these are just three common approaches to interpolating that, but somehow they all share the property that I can parameterize my continuous trajectory, u of t, with a finite set of numbers, u0 through u5 in this case, and on to some amount of time. And that also means I'm only parameterizing it over some finite interval, right? Let's say 0 to t, right? Okay, so once I have that, now I've got a numerical sort of problem that I can write down, right? So given this, let's give our first trajectory optimization algorithm. Which is what we'll call it direct shooting. So if you give me x0 and my finite parameterized, say u0, u1 through un, then I can numerically simulate. That's everything I need to numerically simulate the dynamics. Right? And I can evaluate the cost, jx0, over that finite interval, right? And that cost depends on all of these initial values. It depends on x0, but it also depends on u0 through un. Okay? But that's an easy thing to do, right? I can always, we've been numerically simulating our robots for a while now, and this is just, given this parameterization, I can certainly numerically simulate it. So what you should have in your head now is that this cost for a particular x0 depends on some finite number of decision parameters, u0 through un, right? So what I have really is a function now. If I write down u4, let's say, and I look at how j of x0 changes for different u4, and of course there's another axis, there's all of my u, so I have a different axis, but if I look just along a single axis, then j is some complicated, possibly non-smooth function of u4, right? And again, if I had to look at every possible value of j everywhere for every possible u, that's only going to work if I have a small number of u's. But what I can do by simulating what I'm doing is I'm looking at a particular u. So right now, let's say My initial guess is this particular u. I can, by simulating, what I'm doing is I'm evaluating the function j of x0 for some particular nominal value of u. Okay? And what I'd like to do is somehow take that evaluation and move down and try to find a minima, a local minima. Right? Have an algorithm that walks down here. Now, one way to do that is to, when you evaluate u at this point, not only evaluate its value, but evaluate the local gradient at that point, right? So I'd like, if I can find the gradient of the function at that point, then I can try to walk down the gradient, move in this direction until that gradient goes to 0, right? So if you remember last time, we'll do a little extra work to compute the gradients, partial j x0, partial ui for all I, okay? But the cool thing is, the magical thing is, that computing this is surprisingly efficient using the adjoint equations that we talked about last time. Okay, so we can do a little extra work using the adjoint equations to, and if you remember how those worked, I simulated forward to get my solution x, given x0 and u. I'll simulate forward to calculate x for the entire trajectory, and I'm going to simulate backwards these adjoint equations to get partial j, partial u. Okay. Once I have that, I have an estimate of the slope. I'd like to somehow move down here. Now there's a couple algorithms for doing that, but almost never these days do we just do simple gradient descent. Typically we'll have some better algorithm. So let's talk for a minute about nonlinear programming, nonlinear optimization.
Great. So today we're going to talk about nominally humanoids, but maybe more generally we'll talk about what you can do if you have a highly articulated walking robot. Okay. You could have told me that. It was up before. Yeah, I think it was up before. There we go. Thank you. Don't hit help. It's the last thing you want. Okay, so today let's talk about, well, the topics we'll talk about are nominally discussed in the humanoid robotics literature, but really I think they're valuable for any sort of highly articulated, you've got lots of joints, lots of motors. Articulated.
So give us what we're going.
Still recording. Yes. Thank you for checking. Okay. A highly articulated, let's say, legged robot. Okay. All right. So we've talked about passive walkers and hopping robots so far. And these really do paint for you, I think, the picture of the fundamental dynamics of walking, right? So
I think the story about the exchange of energy with potential and kinetic, the prevalence of the dissipation to the ground at a contact, and the way that you have to think about contact in your planning and control. These are really the fundamental stories in walking. Okay? But if you look at that literature and you look at what we've talked about so far, and then you look at the sort of published literature on walking robots, there's this huge disconnect, right? The things that we haven't talked much about yet, like the zero moment point idea that that I mentioned, these are what right now dominate the literature in walking robots. So the goal for today is to put these two together, to try to penetrate a little deeper into the idea behind the walking algorithms that people are fielding on big humanoid robots today, how we can understand them in the light of the optimization-based tools we've already developed, and just make sure you understand that story. And we'll give some fun demos. Okay. All right. So. Before we start actually talking about legs, I want to have a different model in your head, okay? So maybe call it a hovercraft or a satellite in gravity. But I want you to think about this. I want you to think about, you've got some rigid body, okay? It's flying through space. It's got a mass. It's got an inertia, okay? And you have some thrusters, okay? So I don't know what a thruster looks like, but something that gives me a force. And this is, maybe I'm pushing on the world, but it's pushing on me in the other direction, obviously. So I've got something with thrusters coming out, and I've got gravity coming down. And maybe I'll have more thrusters than that. We'll see, okay? So this is, it's just a toy model, and that's meant to be some rigid body, not necessarily a square. Okay, and our goal for this toy model here is to move the center mass, this mass and inertia. You move your rigid body around, right? It's to move, relocate or stabilize those positions. So let's give it a coordinate. We'll say. Maybe I'll do it in the XZ plane just to remind us that there's gravity. XZ, and then we'll give it some angle of the rigid body. Data, okay? So we want to go to move around and stabilize the position, X, Z, and theta. All right, so the cool thing is, I can write the dynamics down for this. It's pretty easy. Okay, so I've got mx double dot is just the sum over all the thrusters of the x component of the thrust. F equals ma, right? Z dynamics are similarly simple. It's the z component of those forces, and then there's a gravity force too on the z direction. And then there's some term giving me my angular acceleration, rate of change of angular momentum, which is going to look like Ri cross Fi, and the y component of that, if you will. So this is, the thrust is happening at a vector Ri, R1, say, and R2. So that's the location of my forces, right, is described relative to that point. Yeah? This is a cross product. This is a vector. And I just want this is also a vector, of course, and I want the y component of that. The one coming out of the board. Yeah? Okay, so if I think of this as a control problem, maybe my control input is is my forces. I can control the forces. And as far as things go in this class, this is actually a relatively easy control problem, right? So what do you notice when you look at this? Well, first of all, it's a linear system. Well, it's an affine system. There's some extra terms coming around, right? So this is a, the dynamics are affine. Okay. So what does that mean? So that means that I could actually stabilize this thing with LQR if I wanted to, right? In fact, if I have some desired trajectory that I want to stabilize, I could do TV LQR or right, time varying LQR. Yeah, I mean, you could ask it. I could. Maybe everybody's got the same question if you want. But.
He was just asking because the way that the forces are drawn, it looks like they're almost going to the center of mass.
Since it's only under reduced rotation, they're not
That's right. Yep, yep. And in general, they're arbitrary right now.
Yeah.
Yep. For the toy model. Okay, and then maybe I can make it more interesting. So maybe the thrusters aren't very good at sucking; they're only thrusting. So maybe I could I could say, for instance, that all Fi had the has to be, maybe they always have to be pointing out. However, I want to write that. But maybe I want to have some directional unilateral constraints on. And then I could still do some nice planning. For instance, I could do, if there are linear constraints on this, if there are bounds, let's say I put it under element-wise, have some limits, then I can still do nice planning and control with this, right? With the, for instance, the constrained, we talked about linear, the existence of linear model predictive control as a solution for linear systems with constraints. Okay. So in general, this is a relatively easy control problem. Okay. And you can imagine that that maybe if I've only got 2 thrusters, then it might be hard to sort of balance myself with the 2 thrusters. But again, I'll know if I can stabilize it or not because it's a nice linear system. Yeah.
What's MPC, sir?
This is model predictive control. I really only talked about it to the extent that I mentioned that I wasn't going to talk about it, but it is the extension of sort of LQR for things that have inequality constraints. Okay, so you guys like that model? We got a spaceship or whatever, but it's in a gravity field. Got some thrusters out there. Easy to control. All right, so let's make it a little bit more interesting. Yeah. So let's say I've got now I've still got my thrusters. Okay, but now let's say I have way too few thrusters. Let's say I've got let's say I've got too few thrusters. Maybe I only have 2 and I'm trying to stabilize in three dimensions or whatever, okay? But I'm allowed to move my thrusters, all right? That's the new game, right? Okay, so with one constraint, right? So, I mean, if you imagine it as a spaceship, and you send your crew down to move the thrusters, maybe they don't like moving a thruster when it's turned on. So let's say there's a rule that you're allowed to move the thrusters if you want, okay? But you have to turn them off if you're going to move them, okay? That's our game, right? All right, so maybe I'll write that down as I have a model now where the control inputs, same model I wrote before, but the control inputs might be F1, F2, but also R1, R2, for instance. And maybe I'll put in some constraint, for instance, that the force has to be 0 if the, or the velocity has to be 0, which you could write, for instance, like this, that either the force is 0, the magnitude of the force is 0, or the velocity is 0 in order for that constraint to be held. Okay? But this suddenly is a much harder problem because, well, this is a non-convex constraint. This is an either-or constraint, right? So if I were to plot it sort of in my, R dot and F, right? So I'm allowed to have F be positive, or I'm allowed to have velocity, but I'm not allowed to have anything else, right? So you can think of that as that's a non-convex constraint, right? So something in here, in the interior, the combination of those 2 points, the convex combination of those 2 points is not necessarily in that set, right? So that's a harder planning problem, a harder control problem. Okay, but a good one, right? If I've got a spaceship with moving thrusters, that's a sort of a problem you'd like to solve, right? So, and we have some tools to deal with that. And you could do a variation. Maybe it makes sense to write the positions of the thrusters in the local frame. Maybe it makes sense to write them in the world frame. That's a simple variation, okay? But this is sort of the problem I want you to have in your head. You're flying through space. You don't have enough thrusters to get to do everything you want to do, but you're allowed to move them, okay? All right, so now let's add even a few more constraints to it, right? So what if I could only, let's say, in addition to not being able to move the thrusters to turn them on when they're moving, but let's say I have some additional constraints like I'm only allowed to turn them on when they're in a certain region. Okay, so let's say when I put my thruster in a certain region, then I'm allowed to turn it on. Okay, but if it's outside those regions, not allowed to turn it on, right? Yeah?
What force do we use to move the thrusters, and is there limits on how fast we can do it?
So we could start putting down like a velocity limit on R dot would be a reasonable thing to add. Yeah? That's a good thing to add. Maybe I can call it Vmax or something, velocity max. Good question. Otherwise, it's easier again, right? Okay. So now you could sort of think about, let's say maybe I'm flying through space and I can, the game is going to be, okay, let me put my thruster here, turn it on for a little bit. Maybe I'll move it over here, turn it on for a little bit, move it over here, turn it on for a little bit. All right, can you sort of see where I'm going with this? It's hokey. But I think it's exactly the right way to think about walking. I think this is exactly the right way to think about walking. Everything else is confusing. This is the problem in walking. You have a center of mass, you're moving through the world, right? And you have feet, okay? Your feet can produce force, okay? But they don't produce force when you're moving them to the next spot, right? They can only produce force when you got them stationary. You can push on the ground, okay? And guess what? There's constraints on where I can put my foot. Actually, when I stop my foot in the middle of the air, it's not so good at producing force, right? There's a few places I can put them down in the world where I can trust them to produce force for me, right? This is the walking problem, okay? A hokey version of it, yeah? So here's my, this is really the fundamental problem in walking. Think about a robot with massless legs. So now I've got my robot, which has a mass and an inertia, right? And he's got some legs coming down with triangle feet, because I'm not an artist, right? And he's got another really long leg over here that, maybe he's right? So when he's in these configurations, he can produce force. You can think of it as him pushing on the ground or the ground pushing on him, whichever view you like, as long as we get the equations of motion right. But let's just keep drawing it the way I was drawing it before. Okay? And when my leg is swinging through the air, no force. Okay? And yes, there's going to be some limits on how fast I can move my foot to the next spot. This velocity limit that Pete asked about, absolutely, right? And now you can see the sort of the constraints are there might be more natural descriptions on the constraints of the forces I get out. For instance, I might have friction constraints. So for instance, maybe the magnitude of my forces parallel to the ground has to be less than or equal to the normal force perpendicular to the ground. So this would be a simple model of friction, a friction cone. Okay, well, this is a coefficient of friction. Why is that a friction cone? That says my forces at my points can only live in some cone like this, right? It lives in that, but I can't expect to get, if I'm not putting any weight on the ground, I can't expect to push horizontally in the ground. It's a reasonable model of Coulomb friction. That is the Coulomb friction model. Okay, so so good. So this is my problem now, and the dynamics I wrote down are exactly the same as the satellite problem, right? I just have a couple more constraints on my forces. Maybe I have a constraint on how fast I can move the foot, but that satellite problem is really the walking problem. Okay, so far I just talked about a single rigid body. So what if I want more than just a single rigid body? If I had mass in my legs, for instance. So I'm just going to change my mass. My point mass here is going to turn into the center of mass, which is going to be configuration dependent. Okay, and my inertia, the generalization, we'll call it the centroidal momentum matrix. Okay, and it's again configuration of the robot dependent, where my center of mass is. But actually, otherwise, the equations of motion I gave you on the previous slide are basically unchanged. Okay, so I could do this. I could talk about the dynamics of the center of mass using those same linear equations, plus constraints on forces, and then if I have to start moving them, possibly constraints on R dot. Yes.
You're not worried about like what the state of the angles of all the joints are, just be really powerful actuators, or
That story's coming, but it's not here yet. So I'm saying Q is all the joints of my. This is
yes, that maps into the center of mass and stuff. But we're
right.
not worried about controlling Q directly, only how it affects.
Oh, good. So I'm not specifying any objectives for my joint angles yet. I'm just saying that I can describe the dynamics of my robot, my center of mass, and centroidal momentum with simple equations, right? And you're right. So that means I haven't specified in my design yet anything about the joints. Good. Okay, so this is not, I want to distinguish. Some people, I think, talk about these equations that we're going to get into, the ZMP and the center of pressure and all these things, as a simple model for walking. It's not a simple model. This is the governing equations of the center of mass of my robot for the real robot. There's no simplifications made here yet, except that I'm only describing the dynamics of the center of mass. I'm not describing the dynamics of the joints. Okay? Good. All right. Now, a couple special things happen. If I'm willing to make the terrain flat, then that's an important special case that we can look at. Okay? Today we get to talk about manipulation. I defined running and walking and everything. So I looked up what the Handbook of Robotics used to define manipulation. Yeah. So manipulation refers to the process of moving or rearranging objects in the environment by establishing physical contact and exerting forces and moments. I like that definition. It's a good definition. Okay. So here's the cool thing. The problem formulation is exactly the same as walking. Right? So the picture I drew last time, I'm going to draw it again. Right? So I've got a rigid body here. It's got a mass. It's got an inertia. I'll parameterize it in the plane with x, y position, maybe an orientation theta. And I've got some forces I'm going to exert on that. The only difference is I'm going to point the forces in instead of out. That's not a major difference, right? That's just a sign flip. F1, F2, F3, let's say. And my goal is to take some initial pose of my object. Maybe and of my robot. We'll call this, let's just get some notation out. I'll call this Q object. I might just write QO later to be shorter. And Q robot. Possibly just QR later if I'm going, yeah. And move it to some target position. Let's say Q desired object. Maybe I don't care where the robot ends up, but I want the object to have moved, yeah? So now, this time, we started off with magical thrusters off in the air that could move. Then we revealed the secret that they were actually legs. This time, maybe they're not legs, but they're fingers. Okay, but really, the higher order bit is that if you know how to do walking robots, you already know how to do manipulation, right? That's a little jab at all the manipulation people in the audience here. But and the manipulation people say if they already know how to do manipulation, then they know how to do walking. That's less. I don't know. That's also something you could say. You know, I guess the problem with both of those statements is that we don't really know how to do walking or manipulation. So you know, the transitioning from one to the other is still tough. Okay, but the problem formulation really is shockingly similar, and we're going to see that there's a few places where the abstractions we used, for instance, in the last lecture, are going to be the same abstractions that are helpful in manipulation. For instance, this model as a single rigid body exposed to forces, and separating the problem of reasoning about the forces, planning the forces first possibly, and then reasoning about how your robot has to generate those forces. You can sort of separate the problem the same way we did in the walking, in the most recent walking lecture. Worry about the kinematics of the leg in a second pass. First, let's just plan where I'm going to put my forces in the world. That analogy moves over nicely into that's very similar to what you see in the manipulation world. There are some notable differences, not so much differences in the problem, because the problem is the same in many ways, but sort of different focuses, things that the manipulation problem brings to light that the walking people haven't worried about so much, and vice versa. So let's say different areas of focus. So, I'd say one is that the idea, so last time we tried to sort of decompose the problem, like I just said, into planning the forces and then worrying about the kinematics. I would say the division of kinematics and dynamics in manipulation is in some sense even more complete. You can actually, people are very successful doing a lot of work in manipulation without thinking about anything about the dynamics, because you can sort of separate out, the dynamics don't come into play until you actually start making contact with the object, and a lot of maybe the hard kinematics problems of avoiding the world and everything happen before that. And you can decompose these even more completely. Okay, a second sort of, when you do get into the dynamics of manipulation, another sort of different area of focus is that the manipulation community tends to deal with more sort of richer contacts, more contact with more complicated geometries than the walking. I mean, with walking, I'm sort of happy to say I've got sort of my heel's going to touch the ground, my toe's going to touch the ground, and that's good enough. And I'm not really worried about walking on non-convex surfaces where I might rock or over. I mean, some people are, but the bulk of the community's been able to get away without dealing with really rich interactions. If I wanted to, I don't know, do an earthworm kind of behavior on the ground with my robot, where my elbow's touching, my knees are touching, my belly's touching, all these things, then that could be a richer model of contact. But in walking, we've gotten away with sort of having a few contact points, and they're mostly hitting, flat-ish ground so far. In manipulation, that doesn't feel as true, right? So in manipulation, I could manipulate things by just touching only with my fingertips, but typically the objects are non-convex from the view of the robot here, and I tend to have more sort of richer grasping. I might touch with the whole geometry of my hand might be touching, or might be touching in more sort of complicated ways. And so the tools from manipulation have dealt with the geometry and even some of the dynamics of contact in richer ways. So sort of more contact and richer models of contact. So I might worry about a cylindrical finger interacting with a cylindrical cup. And in walking, I would have just said it's a point that touches the ground, right? And we'll talk a little bit about both of those today. There's a third one that I won't get to yet today, but we will talk about before the end of the class, which is that in manipulation, there's a big focus on uncertainty, right? So in manipulation, I tend to be picking up things I don't know everything about, right? So I might not know the exact geometric model of this thing. I certainly probably don't have a perfect estimate of its a moment of inertia. If the thing I'm controlling in the walking case is my robot, then I might have taken the time to build a fairly accurate model, and so my uncertainty is less. Of course, there's uncertainty in the terrain, but the focus has been in walking more on the stability problem, right, of balance and things like this, whereas I don't really have to worry about the stability of my hand. I worry a little bit about the stability of my object, but it's simpler. And in the manipulation, relatively, they're worried more about uncertainty, about dealing with the different types of uncertainty. And we'll at least talk a little bit about the tools there when we get into the estimation and statistical modeling kind of questions in the class. So there's more focus on uncertainty and relatively less on stability. But of course, uncertainty matters for both problems and stability matters for both, and there's crossover. Okay, but just culturally, there's been more people talking about uncertainty in the manipulation world. Okay, so let's see some of the implications of these. So I do think that there's you can sort of get farther in manipulation without worrying about the dynamics. I think if you wanted to start doing human-like manipulation, then I do think you need to think about the dynamics. And by the way, the dynamics are sort of under-actuated by definition, right? So I've got an object in the world, it's got no motors, no actuators attached to that, and I've got to move it around, right? So the dynamics are interesting because they're under-actuated, right? Okay, today we're going to start the next topic, which is feasible motion planning. We've been alluding to it for a few lectures now. Okay, so let me just make sure we have perspective since there's so many algorithms and ideas kicking around in the class, right? So we've already talked about a number of approaches to motion planning. Certainly, dynamic programming is an approach to motion planning, where we gave a few analytical solutions like LQR in special cases and the minimum time in special cases. One case. And then we talked about numerical algorithms based on graph search, right? The other big version of motion planning we've used in class has been trajectory optimization. Okay, so these tools will solve an optimal motion plan for the discretized system, right? But the big objection to them, well, there's the two, were that the discretization, the errors could be hard to bound, right? It was hard to say something about the continuous system, and that it didn't scale well to higher dimensional systems. Doesn't scale. These trajectory optimizations do scale well. But they're local solutions. And what that means in the context of today is that they're not guaranteed to give you an answer, right? So for instance, if I'm planning for my robot that's operating in a maze, I don't know, give myself a simple maze here. Let's say my robot is here, and the goal is here, okay, and I've got obstacles all around me. If my trajectory optimization is currently considering trajectories over here, and it's trying to pull itself towards the goal, it's very likely that it will not return an answer even though an answer exists. It will just say, sorry, I failed, right? So the goal for today is to come up with algorithms that will return a solution if it exists, and will potentially scale to big complex systems. But we're going to give something up in the process. The thing we're going to give up is the optimal. Okay? So when I say feasible motion planning, what that implies to me is that it's as contrasting against optimal motion planning. We're going to try to find any old solution if it exists, but I'd like to have an algorithm that is complete in the sense that it will find a solution if it exists. Is the out-of-focus projector crippling, or is it okay? It's okay? Yeah.
So the example that you gave, doesn't that more have to do with the length of the planning horizon rather than the solution being
Even if I was allowing it to stretch in time, you could imagine even more, trapped solutions. But my, incremental changes to this this trajectory are going to run into a constraint and won't likely back up and come around and come over here. The other way I've drawn it before is that if I've got a trajectory that's currently going left around the obstacle and the right answer is to go right around the obstacle, it's unlikely that trajectory optimization is going to jump from one to the other. Right? Simply because it pictures that as a constraint violation and won't try to look at certain solutions over there. Yeah?
When you say give up an optimality to find a solution if it exists, and are you saying that you'll find a global solution if it exists, or a local solution?
It will find a trajectory if it exists, and there's people that have been working on putting optimality back into these frameworks, but initially we're not going to worry about it being a locally optimal. It's not going to have any objective function, except for, I'll write down the exact problem formulation, but just find a path if it exists from the start to the goal. Okay? And the idea here is that we're going to do motion planning as a search problem. All right, so let me give you that problem formulation. So let's say we have our dynamical system, x dot equals f of xu, or if we're willing to live with the discretization, it can be easier to write things down as the discrete. Sorry, only time discretization, but continuous x and u. And we can write down the discrete time dynamics like this. We're given some initial state. And we have some goal state or goal region. And I would like to find a trajectory, a finite trajectory, which satisfies those if it exists. The thing I'm leaving out is any objective function, saying that I'm going to somehow have preference between there. And we can work them back in, but the first idea is let's just leave them out, okay? So the algorithms we'll talk about here are going to potentially scale to complex robots, potentially giving some guarantees of completeness, but we're going to give up certainly global optimality, and we'll think about what it means for local optimality. There's a great book on these topics. Planning Algorithms by Steve Lavelle. It's actually free online. And Steve will actually be here soon giving a robotics talk in a few weeks to tell us what he's been doing at Oculus Rift. Okay, so let's just give you a little perspective. So I say motion planning is going to be a search problem. Actually, so one of the algorithms we'll talk the most about today was originated by Steve Lavelle and James Kuffner. James is now at Google Robotics. He's just announced that he's replacing Andy Rubin at Google Robotics. So these guys have done very well. I remember seeing a great talk by James when I was starting out, where he came in and he was going to talk about his robot motion planning algorithm, and he gave this introduction, which was, artificial intelligence is search, right? This AI is a search problem. And really, there's a long history of people talking about AI as search. If you date back to some of the original problems in artificial intelligence, like Samuel's checker players and the chess players like Deep Blue, there were theorem-proving algorithms. There's IBM Watson. All these. There's sort of all these big ideas where we're going to say that intelligence is really just the ability to do search very effectively, and there's lots of incarnations of that. But it came down to having very effective graph search algorithms. That's what made it possible for a computer to play checkers initially, as well as a human. Eventually, chess, as the search algorithms got a little bit better and the computers got a lot better, right? And the like, right? So there's a long history of graph search. Right, so I talked about dynamic programming as one graph search algorithm, which basically solved the search problem by very efficiently computing the cost to go for every possible state simultaneously. That was the big trick, right? But there's a whole literature of algorithms that do graph search. I mean, the problem with DP is that it doesn't scale to do that for every possible state when the number of states gets very, very large. So there's a really nice question: is can I find the shortest path from the start to the goal of an enormous graph without visiting every possible node in the graph, right? And there's a lot of good algorithms that can do that. And I just sort of want to pay them lip service here. But there's algorithms like A star, you might have heard of, which use heuristics and pruning to be able to search and find even optimal solutions, but without visiting every node. And there's a few key ideas in that world we'll ask you about, at least one of them on the problem set. Other things you'll see in the robotics literature, D star is a variation of A star that can run even if your robot's moving around and the world, your sense of the world changes. You can dynamically replan A-star type solutions. But there's just, I want to call out to a rich literature of graph search algorithms that are based on an idea of heuristically exploring the space and trying to find a path to the goal without visiting every possible part of state space. Okay, we want to do the same thing, but for me, for control type problems in robotics, the problem with these algorithms is they're always living on the discretized system, the state discretization. They always live on a graph. And we want something for our robotics. We need something that lives in a more natively in a continuous space. Okay, so one of the ideas that Steve and James had early on, you remember what my projection was of the discretized states, right? If I have some state space, x1, x2, and I built some graph, of states here, right? I built some graph on top of my state space. One of the complaints that I had initially was that if I actually look at feasible control inputs, they don't necessarily land directly on nodes. So that discretized system is always an approximation, and it was hard to reason about that, right? So one of the early ideas that came online for the more natively continuous systems was, let's build the graph. We'll still build a graph, but we'll build it sort of dynamically. We'll let the system, we'll sample from feasible points on the, feasible actions, and we'll just let it grow dynamically, right? So instead, let's think of an algorithm that starts off with a single node, and I'll sample, I'll pick a random action, U, and wherever I land, I'll build a new state, right? I'll sort of organically build my graph. Based on random samples. Right, so that's a really nice idea. So, and you can imagine if you want to just keep building up your graph, then maybe an algorithm could be, I'll just pick a random node on my graph, pick a random action, grow it. Next time I'll pick a different random node, I'll pick a random action, grow it. And one of the nice things about this is I'll end up with a set of nodes that are only feasible. They're always feasible points. I've always got, whatever trajectory I have is a feasible trajectory. And it'll eventually try, if I pick something at random every time, I'll eventually have tried every possible action from every possible state, and I'll get some graph that maybe can find a path to a goal if it exists, right? And really, if these all originated from a single node, then maybe the graph is actually a tree. And that trivial algorithm has some nice properties, right? It's not only is it always feasible, you'll eventually every path here is a feasible path, but also it's a complete planar, probabilistically complete is the sort of official way to say it. As as time goes to infinity, as the number of nodes I add goes to infinity, I will eventually, with probability 1, if a path exists in my space that gets me from the start to the goal, I'll eventually find it. This is the monkeys at the typewriter approach to finding it, but it's the way to find it. I'll just try every possible state from every possible action, and I'll eventually get there. Okay, so it's natively continuous, always feasible, and even probabilistically complete. Okay? Very, very simple algorithm. Pretty cool things that you can say about it. But there's a problem with this particular algorithm. Okay? If you start running it, then when Steve and James started running it, and they wrote this in their paper, they would start with some initial state, let's say in the middle of some state space, x1 and x2, or even a configuration space if they're just doing kinematic planning. And they'd grow something to the edge, and then they'll pick a point at random, they'll pick a random direction, they'll grow something. And they ended up with a whole bunch of graph points that were sort of right on top of each other, right? And you'd have a million graph points over here, and it took a really, really long time. If your goal was over here, it sort of would take a really, really long time to eventually find your way there, right? So this turned out to be, although it's theoretically complete, a completely useless algorithm in practice. Okay, that's a caution. Steve Lavelle likes to say that probabilistically complete is sort of an easy property for an algorithm to have, potentially useless because it could take forever to find. So that inspired, so today, instead of throwing a bunch of new material at you, the goal is to talk, it'll be a little fun, I hope. We're going to do running robots today. And it's going to sort of practice the materials you've already seen and tell you all about something a little new. Okay, so today we get to talk about running. And mostly robots, but maybe not all robots. Okay, so most people would think that running would be much harder for a robot than walking. It's kind of interesting that historically the running robots worked well before the walking robots did, right? So it's not to say that running is easier, but somehow experimentally it was easier to demonstrate. So the hopping robots I showed you on day one, which we'll talk a bit about the control behind those hopping robots in the lecture today, happened in the early 80s and were extremely dynamic at a time where the walking robots were still shockingly slow and the like. And there might be a couple reasons for that. I mean, I think one of the reasons is that running is really somehow fundamentally about your center of mass dynamics and all of the details of sort of your leg kinematics and the way your foot interacts with the ground and everything are somehow minimized, I think, when you're just trying to move quickly through the world. Sometimes moving fast is easier than moving slow. It's easier to stabilize a fast motion in cases. And I think in particular, it turned out to be that you could get away with pretty simple robots in the sense that they had relatively small number of actuators, small number of links, and could capture a lot of the dynamics of running. They looked like hopping robots first, looked like pogo sticks and the like. Whereas with walking, you sort of couldn't get around having an articulated leg, which meant waiting for motors that you could package like this and batteries that you could carry. It just somehow turned out to be experimentally harder to realize walking robots. Okay, but there's some beautiful work in running, and there continues to be beautiful work in running. And one of the things we're just starting to see sort of in the field now is robots that are mechanically sophisticated enough to walk that are also capable of running. That's only fairly recent that that's come together. For a long time, you either had a hopping kind of robot that was relatively simple and could propel itself around, or you had a big kinematically complicated walking robot, and only in the last handful of years have you seen both. So before we really dive in, I guess I have to tell you what the definition of running is, right? So what's the definition of running? What do you think?
Intermittent.
Yeah, sure.
Intermittent contact with the ground as you move forward.
Right. So
at some point you're not touching the ground.
Have the existence of an aerial phase, you're going to say the same thing, the first and simplest definition, I don't know why my pen makes me look like a crazy today, but I'm not going to change it. Unless that becomes really distracting, I think it would take a recalibration to change that, but my writing is not quite that bad. Okay, definition one is the existence of an aerial phase. Some point in a quasi-periodic motion, let's say, you have no points of contact with the ground. That's absolutely a good, reasonable definition of running. It turns out people needed more sophisticated, or a little bit better definitions of that, because there's all these counterexamples that don't quite look like walking, look like they should be called running, but don't necessarily have an aerial phase. Anybody old enough to remember Groucho Marx? Yeah? So there's actually scientific papers that talk about Groucho running, because he has a way of running, which I have too many cables attached to me to demonstrate, where he moves along in sort of a clear running gait, but his feet never leave the ground. Okay? So there's another definition of running. Does anybody know the other definition of running? The biomechanics definition of running? say definition 2, it talks about the exchange of kinetic and potential energy. Okay? So specifically, walking, the motion, the transitions between kinetic and potential energy for walking sort of looks like vaulting. So some of the earliest models of walking really thought about your center of mass sort of vaulting over your stance light. So your center of mass goes up and over during the stance phase. Okay? So your potential energy peaks during mid-stance. And running, a very useful definition of running, is when the opposite happens. When your stance leg actually compresses during the stance phase, and you have an opposite exchange of kinetic and potential energy. So in this cartoon, I mean for the dot to represent your center of mass, and maybe in a generalized way, this could represent some center of pressure on the ground, which we mentioned quickly when we talked about ground reaction forces before. Some single point to represent the net force on the ground. Okay? And so in running, your potential energy actually drops through mid-stance. Okay? And there's all these really great exceptions. You know, Groucho Marx is one of that's sort of become famous in the biomechanics literature because someone wrote a paper calling it Groucho running, and it somehow stuck. But there's actually a lot of great examples. So first of all, the question about the aerial phase was initially, it turned out back in the day, people didn't actually know if animals were getting aerial phases. And there's this famous story of Leland Stanford, of Stanford University, who basically had a bet going with one of his friends that his racing horses actually obtained an aerial phase during the races. And nobody knew, because cameras back then, if you took a picture of a running horse, were just a blur, right? And so Edward Muybridge was a radical photographer of the time, and he was paid to basically invent a type of photography that was allowed him to take pictures like this. Basically, he invented the shutter for a camera, and was able to take some of the first pictures that definitively showed an aerial phase, even in a racehorse. Yeah, and he's actually credited with as being one of the fathers of motion photography now, right? But there's all these other quirky cases too. So that was in the late 1800s. 1878 was this first sort of famous picture. Even just about 10 years ago, people were still debating whether an elephant runs. What do you think? Do you think an elephant runs? What do you think? Yes? Yeah? Turns out the answer is pretty complicated. And the way you figure it out is you start motion capturing horses, okay? And actually the audio on these videos are hilarious. You're like, yeah, trying to egg on this horse, this elephant as he runs around. And the answer turns out to be that most elephants don't obtain an aerial phase. Every once in a while, you'll see an elephant that can actually get an aerial phase, but most of them don't. So then you have to go to definition 2 and ask, what does the center of mass look like? What does the exchange of kinetic and potential energy looks like? What do you think? Running or not running?
Oh, I was going to say that I guess the exchange of the center of mass would be like, it's trying to exchange the load from the front to the back. It looks like it's running, the back feet are running, and the front feet are running, but in between it's kind of holding it.
Did you get all that out of this one video?
Yeah.
That's amazing. So you're actually really, really close. But it turns out if you look at the exchange of kinetic and potential energy, the best answer that these guys could give, they said basically it breaks the mold. But they said if we have to give an answer, we would say the back legs are running and the front legs are walking. Right? And unlike most animals, actually all of the legs are breaking at every step. You know, they're just doing so much work to hold up their mass that they're totally bizarre. Their front legs are walking and their back legs are running. That was the official Nature paper result. Okay, so there's no simple answer for, you know, there's always these corner cases. But there are simple models, okay? So not surprisingly, we're going to be able to understand a lot of things about running by looking at a few simple models. So today we're going to do simple models of running. And we'll get back to some of the robots that have been built which match the simple models better than you see in walking robots. This is like the Halloween font or something. Maybe it doesn't look as bad to you up there, but in high resolution it looks ridiculous. Okay. So let's talk about today about trajectory optimization with convex optimization. Okay, so all right, so here's the motivation. So the trajectory optimization we've written down so far has been as a nonlinear program. Okay, so it's great. It can handle nonlinear dynamics under actuated dynamics. It can handle nonlinear, even non-convex constraints, right? For instance, obstacle avoidance, we'll talk more about that today and see how that fits in. But the solvers aren't guaranteed to find a solution, right? You fail to find a solution even if one exists. So last time we tried to address that by telling you about one of the algorithms from randomized motion planning, the RRT. Which gave a form of completeness, you know, completeness in the sense that if I wait till time goes to infinity, I'll definitely find a solution. But in practice, these are effective effective planners for very complicated domains, and they are probabilistically complete. So I feel like I talked to a bunch of you afterwards, and maybe just by virtue of the order that I chose to present them, you know, trajectory optimization first, and then RRT comes in looking like the solution. I think they both have their place, and they're good for different things. But actually, our group uses more trajectory optimization than RRTs. You know, I don't want to give you the impression that the RRTs somehow fix all the problems with trajectory optimization. I think they're both different tools. They have different virtues, right? The RRTs give you random-looking paths and need some extra work afterwards. Typically, they take a lot longer to solve, but they solve a broader class of problems. Okay. But there are some trajectory optimization problems that are guaranteed to find a solution if one exists. Okay. And they can be made to solve a pretty broad class of problems with some extra work. So I want to talk today about that class of algorithms, right? Now, there's various versions of it that we could focus on. I'm going to choose, just so we don't bounce around too much, I'm going to talk about the ones that can be written down as just one particular type of convex optimization, which is a quadratic program. So I know you got to learn about linear programming on your last problem set if you didn't already know it. And we've mentioned quadratic programming a bunch. Let me just give the quick reminder or introduction as it is about what I mean when I say a quadratic program. Right, so a quadratic program is something that I can write down as a minimization of some quadratic function. And I can have linear terms in there too. I could have constant terms, but that would not affect my solution, so I'll leave them out. Subject to linear constraints. Now, almost always when we say quadratic program, we actually mean a convex quadratic program. The ones we can solve effectively are when Q is positive semi-definite. Then there's efficient algorithms to solve that, because it's the convex case. The non-convex case is NP-hard. So there are tools to solve it, but they're not in the realm of convex optimization. So the picture you should have in your head here is that you have some decision parameters, let's say Z1, Z2. These linear constraints give me some polytopic region. Each one of these constraints is a linear constraint, a half-plane constraint. So it cuts off, says maybe I'm on this side of the plane. Another one says maybe I'm on this side, maybe I'm on this side. And you put them all together, since they all have to be satisfied, I get some region that's my convex region of feasible points. Satisfy those constraints. And I also have some quadratic objective, which is quadratic bowl. It sits on top of that. Even my colors aren't going to save me here, are they? But some quadratic bowl that sits on top of that. And I have to find within the set of feasible points the minimum of that quadratic bowl. And you can imagine that if it's upside down, then that's a lot harder. It could be smashing into any one of the corners, and that gets to be combinatorially bad. But if it's an upright bowl, then I go to the minimum, everything's good. Okay? So it turns out that we can formulate some trajectory optimization problems as a quadratic program. And if we can do that, then then these programs are guaranteed, they're convex optimization, just like we've been saying the whole time. If a solution exists, we're guaranteed to be able to find it and find it efficiently, right? So let's think about the cases where we can write an optimization, a trajectory sort of optimization as a quadratic program. Okay, so for instance, I can write down LQR as a quadratic program, or at least a finite horizon version of LQR. Okay, if I have a finite time LQR. All right, so let's do that. Let's do that on the next slide. So. We'll go ahead and discretize time just to keep it cleaner, but that's not actually required. It's required to discretize your inputs, but not your state. Everything's simpler like this. Okay, so I'll write down my linear discrete time dynamics. And let's try to minimize over some finite time my inputs. Somehow I'm getting extra clicks today. Of my quadratic cost. Okay, so maybe you can see already, but it's going to be pretty natural, actually, to write that down as a very large, potentially, quadratic program, but as a quadratic program. And we can actually do two different approaches to do it, right? You've already seen some different approaches to trajectory optimization. Either one could work here. In discrete time, collocation doesn't make as much sense, but we could certainly do either the direct transcription or the shooting approach. And you can write either of them down, and they're both a quadratic program here. So I could do the direct transcription. I'll choose my decision parameters. I was calling them Z on the other slide, but I'll do x0, I'm sorry, x1. x0 is given. So xn and u0, un minus 1. Be my decision parameters. And then I can just write down some minimize over z, this quadratic function. It's going to be, call it h, some big matrix H, right? Where H is going to look like Q, Q, Q for a while, R for a while, depending on how I ordered them. Right? But if I line up x1, x2, u0, un minus 1. Right, same thing on the other side. Then I could write this cost function as a big, pretty empty matrix. Okay. And then I can write these dynamics down as linear constraints on those variables. Right? So they're equality constraints, but I can write that down as a pair of inequality constraints. Right? So I'll just write less than or equal to and greater than or equal to. That gives me my equality constraints. And A is going to be This A is going to be a big matrix that has those elements in it. This B is going to be, right? Okay, so that works, and I can write down, given a linear dynamical system, my LQR problem as a very big, potentially, in the horizon time of the optimization, quadratic program. And in fact, I can solve it really fast. And QPs are pretty darn fast to solve these days. Okay, solve it really fast. So this one, certainly for any n goes to infinity, has a closed form solution. So I'm not sure. I have to somehow still convince you that there's something good about this, about doing this. The simplest way to convince you, I think, is that given this optimization, I can start doing all the things that I couldn't quite do before. Like I could put in my input limits directly, right? I could put in constraints. And I can still solve it. I can even put in state constraints if I want. Linear constraints, but if I have linear constraints, I can start dropping them on, and I can still solve it, right? The big thing I'm giving up, well, the first thing I'm giving up is I have to solve a big optimization, potentially big optimization problem. But again, that's cheap. Don't be afraid of that. The biggest thing I'm giving up is I'm solving it from a particular initial condition, a particular trajectory, whereas LQR so far we solved for the complete solution for the complete feedback controller. Okay, so one of the things that people do this is often called model predictive control. It's important, I'll put it in blue here. Sometimes this is, you can have a nonlinear version of model predictive control. Maybe this is often called linear model predictive control. And the reason it's called that is because I'm computing, potentially with a big optimization, a control from a particular initial condition. But a lot of times people will implement this online. The QP is fast enough to solve that you basically, I take my current state X, I plan for the next n minus 1 steps what my control action should be. I take the first one, I go one step, I see where I actually arrived at, recompute my solution for the next n minus 1 step, and just do it in a receding horizon way. And that's a way to turn a fast, guaranteed to succeed trajectory optimization algorithm into a feedback controller. Now you have to do that at your own peril for a general trajectory optimization, because you could be marching along happy with your feedback control, and then suddenly your trajectory optimizer says, sorry, couldn't find a solution that time, and you're in some state that you didn't want to be in, and you're stuck, right? But if you have one that's guaranteed to succeed, then this is a great algorithm. Okay? Does that make sense? Yeah.
So why are you planning every time?
Because so this is a trajectory optimization. It's finding a particular set of u's, scalar u's, over time. It's not giving me a policy u as a function of x. So if there was no noise in the system and I moved one step, I'd be exactly where I thought I was going to be, and I could just keep using my original plan. But if there's noise in the system or a disturbance or something like this, I'm off my plan. I'll recompute given the new final horizon, the new horizon, and run again.
So you don't always be planning, only be planning your indefinite state that you can consider.
But in the real world, you're never where you thought you were going to be. So every DT, you replan. You could put just do it every time. Yeah. Because your model's wrong, and there's noise in your sensors, and there's all kinds of stuff. Okay, you could also do this with yeah, sure.
If the time horizon is the next time step, is it the same as deadbeat control?
If
When you arrive at the next time step itself, like is it a subsection of this? Or?
Deadbeat control would be if you asked if my objective was to get to the goal in one step. So if I put in a constraint saying x at time 1 has to be my goal, then the thing that would pop out would be deadbeat control. But this is actually saying, This is saying something, slightly different, right? I can have a different. This is a quadratic objective the way I've written it. Yeah, but it's similar. Yeah.
So how do you impose long-term goals? So you want to reach some certain state in the future, and your horizon is not long enough.
Okay.
So you're just steering towards.
So there's a couple things you can do, but a lot of times what people will do is if you don't have the computational resources to make n big enough, then what you can do is say xn, let's say, tack on some final cost, which would be, let's say, from LQR. So ignore your control limits, ignore the constraints that you can't handle in LQR, and just solve what would be the infinite horizon cost to go. And then I'll think about my constraints for n steps, and then from there on use the cost to go of the unconstrained problem. And that's actually what Scott was talking about. We're setting at n to 1 on Atlas. We're computing LQR for the whole for the infinite horizon, and then just instantaneously taking the cost, the input limits into account to go down to, yeah.
So assuming the system is linear, are the x's here in this case, are they actually like x bar? So assuming it's linear and we follow a trajectory, are the x's here at each case actually the error? Is this actually like, x desired minus where we want to be,
yeah,
or minus where we are?
So that absolutely works. It doesn't matter what your coordinate system is in the linear case. You could either change your coordinates to x bar here, or you could have your objective have a x minus x bar, or x minus x naught, and have some linear terms in your objective. Either one is still compatible. It could be written down as a QP. You get to pick.
Just one more question.
Sure.
Do people have guarantees that you will arrive at a goal with respect to the noise in the noise that you have in your system? Is that the kind of guarantees that people have? Or?
So we haven't modeled noise here. In the LQG case, there are some guarantees if you put in Gaussian noise assumptions like that, and we'll talk about that soon. There are ways to use these in a robust model predictive control way, where you can sort of guarantee that you're going to go downhill in the cost to go from this. And actually, we're going to talk about both of those in the sort of noise and robustness lecture, for sure. But actually, for linear systems, linear plus plus, let's say, linear plus noise, linear plus bounded uncertainty, you are going to have very nice generalizations of this. Yeah.
How do you write your dynamics as AX? Do you use like finite differences?
So I shouldn't have said x there. Good catch. This is z. That's my decision variable z. Yeah. And I really shouldn't call this a. Let's call it a bar or something like that, just to make it different. Good catch.
So if you're actually dealing with a nonlinear system, this is just a linearization. It works well and it's pretty small, like you're locally. But if you want to plan long term, you can only encode like linear dynamics here, right? And you wouldn't be able, you don't know where you're going to be, so it's not completely linearized.
So you're getting ahead, but yes. So
is that why you guys do like one step with Atlas? Because locally you do look like AX plus.
Locally, Atlas is linear.
Yeah.
If you drop in Q, if you know your state,
yeah, exactly.
then the dynamics are actually linear for one step.
Yeah, but like
and long term, it's not.
You'll be somewhere else.
That's right. So the question of how you use this, so you could use this for nonlinear trajectory optimization. One thing people do would be, they call it iterative LQR. You can actually do nonlinear trajectory optimization by picking having your initial trajectory, linearize it, use this. It's like a sequential quadratic programming update, but it's a slightly different update, where you basically use this to say what would the linear system have done if I optimized it,
Okay.
and then relinearize what would the linear system have done. And that is in spirit, very similar to the sequential quadratic programming updates, but it's numerically different. And some people believe it's an important difference. And that's typically called ILQR, or iterative LQR, and that's an algorithm that people have in the trajectory optimization world. And a slight variation of it is called DDP, differential dynamic programming. And it's almost the same thing, but it turns out, so here we we did more than that, actually. We took a linearization of the dynamics and a quadratic approximation of the cost locally. In DDP, you can have a second order approximation of your dynamics and still solve it as a QP.
Okay.
And yeah, and
But when you're optimizing, you like committed to the trajectory that you linearize your dynamics around.
yes, and then you use that as make a one step like that. Wash, rinse, and repeat. Yeah. Cool. I want to make sure you see that you can also write the shooting method down just like this. It also works. So if I were to have chosen my z to be just u0 to un, right? For linear systems, I can just solve away all those extra terms. My xk is just a to the k x0, right? This is just the solution marching forward of a linear system, but it's still, well, it's linear in the initial conditions and it's linear in my decision variables. So I can just stick all this into my cost everywhere I had xk transpose qx. I don't know why it's doing that today, but I can, looks like something from Carey or something, huh? Everywhere I had this, I can stick in this big mess and still have something that's quadratic in my objective, right? And then this, of course, is just adding more quadratic terms. So that's a quadratic program with significantly less decision variables, less constraints. In fact, if you had no other constraints, you could solve it away with least squares. Arguably, so I think for quadratic programs are so robust that it's not a big difference either way. You know, for some of the other solvers we have, the numerical conditioning of your problems makes a big difference. For quadratic programs, the solvers are good enough that they'll scale gradients for you and just take care of that mess.
Will you reach the same solution with the two methods?
Yeah. All right, so let's make sure we're on the same page here. This is a question for you. If I have an airplane, I'm going to draw a silly airplane, sorry. It's got a tail, yeah. And let's say I'm willing to make a linear approximation of the dynamics of the airplane. And I've got a goal here. And I've got an obstacle here. So can I write that down? Let's even say it's a convex polygon. Can I write that down as a quadratic program, the trajectory optimization from my current initial condition to the goal? What do you think?
You want to avoid.
I'm guessing. Sure.
You want to avoid the.
So I want to minimize my my actuator input, let's say, and get to the goal.
If you want it to be in that polygon, you could write it.
Right.
Yeah.
Right. So exactly. So the polygon, you can write down a polygon, the interior of a polygon, right, as a set of linear constraints, right? But the exterior, this is saying that, each one of these lines, just make sure each one of these lines is a linear constraint. If I'm saying I'm on this side of this, and I'm on this side of this, right? The interior of that is a set of linear constraints. If I want to stay outside it, you can't write that down. You want to. That's an or, right? I want to say I'm on this side, or I'm on this side,
or I'm on this side, and you can't write that down as a simple matrix linear constraint, right? Unless, if you're willing to, for instance, let's say I were to say that this is region 1, let me call it, I don't know, S1, and this, let's say this over here is region 2 when I'm on this side, and if I were to be willing to say, for instance, that x0 through xk are inside S1, and then xk to xn are in S2, then you could write that down. But I've had to somehow pick k as the time that I'm going to be in this intersection. Okay, we'll get back to that in a little bit. But I want people to really have a visceral feeling for the fact that that is a avoiding an obstacle is a non-convex thing, and I will not have a convex optimization that gets me there magically, right? It gets me a sort of obstacle avoidance. Okay, so one of the really cool things is that you can do is you can start asking the question. So this is a richer class than LQR now, because LQR gave me infinite horizon or finite horizon if I solve a Riccati equation. We had different versions of LQR, but we never had one that could handle the input saturations or state constraints. This one works for only from a particular initial condition. But you can actually go back and ask the question is, how does this solution to the quadratic program change as a function of initial conditions? And that could sort of give you some sense of what the feedback controller that you would be getting if you were to run MPC looks like. And in fact, there's people that have advocated that okay, MPC works great, but you say it's too slow for your embedded processor. So we'll actually, there's something called explicit MPC, which will try to solve that feedback controller by running MPC enough times and evaluating, understanding the solution basically, and come up with an exact expression, which is the feedback controller from MPC. And that's an idea called explicit MPC. Okay, and the way to think about it is there's another type of problem, another type of mathematical program, which is called a multiparametric QP, basically a parametrized QP. Think of it as just, a QP parameterized, a parameterized QP. It's got to be parameterized in a specific way. So if I were to write a QP, the one we've written down here is a QP that's sort of parameterized by x0. And in general, the form is something that I've got some x0 plus the min over my z, z transpose hz. I'm just going to throw in a bunch of big matrix symbols here. Those letters are not to be taken seriously. They're just big matrices, yeah. debated whether to write that down at all for you, but just to give you a sense of the class of problems that are sort of the multi-parametric quadratic program. It's got a quadratic program on the inside. It's parameterized in a quadratic way by some parameters, which I've written x0 to be consistent. Okay, there's a very important result from the world of MPQP. It's theorem 1 in a paper I'll cite in the notes. And that is that if I look at the solution of this QP over x0, then first of all, the feasible solution, the feasible set, is polyhedral. I'll interpret this for you in a second. The resulting value function it's got lots of nice properties. It's continuous, convex, and piecewise quadratic. And the optimizer, z star, which is a function of x0 now, is continuous and piecewise affine. I'm going to show you pictures that make this click, I hope. So the unconstrained LQR problem, we know had a value function that was a quadratic pole. The constrained LQR is also it's piecewise quadratic. It's still convex. In every segment, the cost to go is a quadratic function, but it's put together with pieces of quadratic functions. The controller for LQR unconstrained is a linear controller. Now it's a piecewise linear controller. Okay, it's beautiful that they can prove this, and actually they prove it in general for these QPs, is that QPs have these nice continuous solutions. We've parameterized them in this way. One of the downsides is that the number of pieces is kind of out of this world, right? So it's upper bounded, which is probably really conservative, but it's upper bounded by the number of possible active constraints. So 2 times the number of constraints. In general, for every possible set of constraints, which can either be active or inactive, I have a different piece in my system. And I'll show you, maybe I'll do it now, but I'll show you that can get big. And so this is in my view, it's a theoretical value and less of practical value, but some people do advocate using this to solve things that I could compile down to a microprocessor, which would be faster than solving a QP on the microprocessor. Okay, so the title of the lecture is Feedback Motion Planning. And listening to your feedback, instead of starting with a broad, big picture motivation, let me start with a specific case study example, okay? So, so you remember on the midterm, I gave you a question about juggling, right? You just had to think a little bit about trajectory optimization of a juggling robot. Let's think a little bit more about the juggling problem.
So juggling is obviously a hugely complex manipulation task. People do it with flair. One of the beautiful things about the juggling robotics literature has been that there's been success in distilling that really hard problem down into simple models. And I really want, as you have thought now about your projects and what you want to do, I think you will be most successful in all these endeavors if you can find a way to capture this thing you care about, this idea you've had, in the simplest possible way, try the tools on that, and then build back up to the complicated model. So the story in juggling is very much, again, a story about the simplest juggling model, which is what I had on the midterm. And then building back up from that. It's called the line juggler. Okay, and it's, you'll remember there was a zero line, there was a paddle and a ball, the height of the ball called B, the height of the location of the paddle was R, and everything works just in the line. So the state space of this thing we're going to be able to write down as B, R, and B dot, and we'll assume that we have direct velocity control of the paddle with some big actuator underneath. So our input is just on the velocity of the paddle. And the other big assumption is instantaneous elastic collisions with some coefficient of restitution. You get most of your energy back. Now we talked about in the midterm about doing trajectory optimization for this, but if you want to do feedback design for this, it's still a relatively high-dimensional nonlinear thing. It's a hybrid system with impacts, certainly under-actuated in the sense that I've got nothing to do to control the ball when the ball's in the air. It's only the moment when it's hitting the paddle that I can have some effect on the trajectory of the ball. Okay? It turns out everything gets a lot easier if we just if we restrict our attention to feedback controllers that take a particular form. So yeah, restitution. Like, so you get the velocity that comes out of the collision is the negative of the velocity that comes in times 0.9, let's say. Right? That's the coefficient of restitution. Okay, so we're going to restrict ourselves to controllers of the form R is, let's say, negative K of B, or more generally, negative K B dot of B. But the point is I'm going to restrict myself to things that are somehow where R is doing roughly what the paddle is doing, but in the opposite direction. These are called the mirror laws. Okay? They're a great idea because they simplify the dynamics considerably, right? So just by virtue of having this sort of mirror law, that I'm doing the opposite of what the ball's doing, I get for free that collisions only occur at R equals 0, B equals 0, B dot less than 0, less than equal to 0, I guess. Right? I'm always going to collide in the same place. The ball's going to be coming towards me. Just all these screw cases go away. Right? And, not surprisingly, the real big win is that suddenly my high-dimensional dynamical system can be described completely on a one-dimensional Poincare map because of this, right? So if now the whole state is
can be described by at the moment of collision by just the value of b dot. Okay? And the cool thing is that very simple laws, even constant k's chosen properly, can give you stable Poincare maps, right? So the hopes that I can keep things all on one page and still be legible, I'll just so I'm in the negative quadrant now, okay? But turns out you get these beautiful Poincare maps. They always, with the mirror law, they're going to go through the origin. And I'll get an unstable fixed point at the origin. But you can get these globally stable, except for that measured zero set, fixed points that will stabilize a constant juggling height. Okay? They say essentially globally stable because there's only a measure zero set where so there's one point in the space where I'm not going to converge to the origin, to that stable fixed point. Okay? So this is one of the classic under-actuated hybrid feedback control problems where people have done really nice work and understood the system and produced robots that can do it. To make the robot, so you can build a robot like this in the plane. In practice, you tend to need to stabilize that out-of-plane motion just because it's a physical system. You can't start it perfectly with zero velocity maybe, or it's hard. Okay, so there's a simple generalization of this. Turns out if my robot is instead of a up and down motion is now a paddle like this, where I have some theta dot maybe moving up, and my ball now has both a y component and an x component. Then I can do almost exactly what I did before, and with some sort of small angle approximations, I can still stabilize this by thinking about how to stabilize both parts. The big idea is I can just modify the collision to occur either just above the line if I want the ball to start to move more this way, or just below the line if I want the ball to move more this way, right? And you can put these things together and get nice, practical, stable juggling robots with this mirror law being the heart of it, and then just a small deviation from it to give me the stability in the out-of-plane motion. And Martin Buehler and Dan Kodacek made all these juggling robots back even in the 80s. This is just showing off doing two at once because, hey, I'm not doing anything when the ball's in the air, so I might as well hit another ball, right? This is on like an air hockey table that's at an angle, right? Just to help it stay 2D. Okay, and then there's of course, the same trick that you did to go from 1D to 2D. You can do that in this direction too if you have an extra degree of freedom in your manipulator and extend it to 3D. And this is Al Rizzi came into the picture, and working with Dan did the 3D version. I might have a particular love for this because my desk was behind the curtain for a little while, sort of. They had done this work before I came, but that robot was at the University of Michigan in the basement when I was there as an undergrad. Wasn't far from the foosball table. Okay, so they got this basic juggling behavior, and then they started. You can imagine a small generalization to that controller, which is very much a feedback controller designed with hybrid analysis and nonlinear control. Right? They could generalize that to just stabilize the zero velocity, so they could catch the ball. Palming, I guess, is an important trick for at least a paddle-based juggling robot. It's non-trivial. Yeah, so they could palm the ball. They could start, and then they started to get fancy, right? They wanted to start putting these things together. Maybe I don't know, I don't juggle very well, but you can imagine, doing more complicated things with the robot. But they didn't, those more complicated things started involving things like collision detection, right, with my leg. And they actually did have beams coming in, and they wanted to juggle this side and then this side, and they did all kinds of fancy things with this. But they needed a mechanism for doing that planning, the collision-free planning, with a system that was a dynamical system to begin with, in which they already had feedback control built in. And really, they couldn't, you couldn't, after you've done these mirror laws and thought about it this way, it's hard to go back to thinking about the full state space of the juggling. It feels like you don't want to throw away all that work you've done. So this was a big motivation. If you think about how do you take the feedback control ideas we've been talking about and the planning ideas that actually people hadn't even really been talking about as much back then, and these ideas of planning and collision-free, how do you put those together in a beautiful way, right? And it's hard, but they had a very, very beautiful picture that they put into their work of how you could put these things together. Okay, and I thought I'd actually pull up their picture. So this is their idea. So Rob Burge came in and joined the group, Al Rizzi and Dan Godacek. They talked about sequential composition of dynamically dexterous behaviors. Okay, and the idea was instead of planning trajectories through space, like we've been doing with trajectory optimization, with RRTs and everything, they're going to take and compose existing controllers, okay, by guess what? Thinking about Lyapunov functions. Okay, so this is really, everything's coming together now. You get ready, okay? So we got Lyapunov functions, okay? They're going to think about their feedback controller, which they've analyzed on the Poincare map. They have a sense of its basin of attraction, right? And they're going to think about each controller that they have, separately designed, as something that takes a bunch of initial conditions and takes it to a smaller set of initial conditions. That's what the goal of my feedback control, right? And we can be precise about that using the language of Lyapunov functions. If I can find the region of attraction, right, and then I know that after some time I'm going to go downhill on the Lyapunov function. Okay, the Lyapunov function can give me metrics for these pre and post conditions. Okay, but this beautiful picture is a feedback control as a funnel that takes things from logical state space to a smaller bit of state space. And then the idea that's very powerful, I think, is that if you can just take multiple feedback controllers and sequence them together in the right way, and have the output of one feedback controller feed into the input of another feedback controller, then you can do more than you do with any one feedback controller by itself. Okay? And maybe if you're looking back down at state space, then what you could do is when you initially had one controller here that just covered a little bit of state space, because it was maybe a local controller or something, maybe you can start building controllers that are valid for a lot bigger part of state space by composing these things together. And we know that the reachable set, or the pace of initial conditions that you can recover from, might not be some simple circle or something like this. Maybe it's some complicated picture like this. But with enough funnels, right, you can potentially fill the space. So there's this big idea, this big idea of trying to take feedback controllers and doing planning with the feedback controller instead of planning with the trajectory. Okay, so today it turns out that's going to connect really nicely to the stuff we've been thinking about with trajectory planning and with Lyapunov functions and everything. It all comes together in a nice way. One of the things actually that was interesting is they proposed this before they had the tools to really build and verify Lyapunov functions, right? They didn't have sums of squares algorithms then. If you go farther into the paper, you'll see that they have scatter plots of data, which they drew circles around and said, they ran it on the robot a bunch of times. They got scatter plots of when it worked and when it didn't work, and they drew a circle around it and said, that's my beginning of my funnel, and that's the output. Nowadays, we can call sums of squares, for computing those, and that's a difference. Yeah.
Do we need to assume something on the bandwidth of the controllers so that they don't cross-talk with each other?
So always yes in some sense, but so there's just a question of how much you have to model in your dynamics. That is just another piece of the dynamical system. So if you were to assume that the bandwidth was infinite and find out that caused a mismatch between your model and the real robot, then I would add more richness to the model to encode the actuator dynamics, for instance. Right? So that's always an exercise in all of these problems, and most of the time where you can get away with, like the time constant of the ball moving and the paddle moving are much lower than my actuator, but you're interested obviously in the space where the actuator dynamics matter. So you'd be finding the place where the actuator dynamics have to be in the equations of motion. Yeah, and we do that for some problems. It just depends on the time constant of the problems. Okay, so they put this together and did cool stuff, right? So this is their sequential composition piece. For instance, you could plan and palm and catch balls, and you could see I had to do some work to find these videos, but I've definitely seen videos of them bouncing, through and over poles, which is sort of under the leg, and things like this. It works. They were able to make it work up to the limitation at the time of being able to estimate those funnels from data. Okay. But the big idea there is that these Lyapunov functions that we've been talking about can actually connect back and be a useful tool for planning. Okay? Okay, let's get started. This is my last lecture for the term. Then I turn it over to you guys. So I want to give you at least a little. Normally I spend a couple lectures on this, but somehow with the project presentations and also just the schedule the way it's played out, I get only one lecture on learning, but we'll do a little bit of learning and try to give you a sense for at least my view of where it fits into the concepts we've developed so far in the course. And I also get to sort of summarize what happened, right? Just to make sure that you guys remember some of this or have it in context, and I get to talk about the bigger picture, right? So let me start with a little bit with that, and I'll put the learning in context with that. Okay, so we've covered a lot of computational methods in the class, right? From DP to local linear feedback. This is in general for nonlinear control and planning, right? So DP, LQR, sums of squares for the Lyapunov methods, like with sums of squares, trajectory optimization, trajectory feedback. We did randomized motion planning a little bit. We talked a bit about stochastic and robust control as an addition to that. Right, and these tools that we developed, basically, they work pretty well. Well, they work to varying degrees. DP will work extremely well for all sorts of problem formulations for very small problems. LQR works very well if it's linear and works okay if it's nonlinear, and so on and so forth. They all have their limitations. They all have their things that they do extremely well. You get to get the intimate details of that on your projects, right? These have been demonstrated in general, on real robots. We've shown their extensions in almost every case to hybrid systems, I mean, they're pretty general tools. For low-dimensional systems, we can basically solve to our heart's content feedback controllers that we could say every initial condition that can get to the goal will get to the goal, given this, and we can give you a certificate saying, giving you some confidence that that's true. But I would say everything we've talked about so far, every single one of these has at least a couple flaws, right? Maybe two big flaws, right? And I want to make sure that I express those and I don't leave you, thinking it. So at least two big flaws. Or assumptions, let's say. Right, so first of all, we assumed we had a good model, right? Or we did robustness a little bit, but somehow we've developed a set of tools which will work best if the model is good, right? If we can come up with an ODE model of our complicated system that we can reason about, right? And for some of the complicated systems, we'd like to write down a PDE, but we really have our best tools are for ordinary differential equations, right? We've basically been assuming that. Maybe, plus some uncertainty, but we've really been pretty model dependent so far. And the other one is we've assumed every one of these methods we've talked about so far is a full state feedback method. Right? We've assumed somehow that we've been able to estimate the state of the system with some state estimation or something like this. Right? So this one means we're sort of very dependent on system identification. And this one means we're very dependent on state estimation. And these are things that keep me up at night, right? It's real. It's true. I mean, we really, we can, in some cases, give certificates saying that we have some robustness to these things. But fundamentally, we've given a model-based approach so far, right? So I would go as far as to say that, for the pendulum, we can throw the book at the pendulum. Every one of these tools, I showed you an example on the pendulum, right? And when it's all said and done, I think our best computational tools come up with controllers that are inferior to the energy shaping control, right? In what way are they inferior? I can give you a better proof in some sense of the trajectory optimization plus feedback plus everything, but somehow if you have a pendulum sitting in front of you and you've just quickly estimated the parameters of the system, you don't know the friction exactly, you don't know, you've got a quick and dirty state estimator that you put on the system and you just want the thing to swing up and balance at the top, you're going to have more luck immediately with an energy shaping pump up controller than something that we've designed so far. And I mean, that's where we're at right now. I mean, I think that we can use these tools. I think the long road is to use these tools and to, for instance, include the state estimation in the model, do verification and control design through the state estimation. To ask in the right way for robustness to the right real quantities, and I think a solution that should emerge through very nice application of these tools would be something like if the best controller is energy shaping, then that should actually pop out of these tools. But I haven't seen that happen yet. I feel like we're getting close, but we're not quite there yet, right? If that does happen, then I think these tools will let you do it for many more complicated systems than the pendulum, right? It just happens that in the very, very simple systems, we have handwritten controllers that we know to be good. But if you wanted to do more complicated systems, these tools will scale, and somehow if we can write down the right questions for those complicated systems, that's where I'm putting my money,
is figuring out the right way to encode robustness and ask for the right thing. But we're not quite there yet. I mean, I think we're on the long road to the right place, but we're still losing to energy shaping. Okay, so I mean, I think that's important to say, right? Let's think a little bit about what it would take to finish that road, maybe a little bit, right? So the problem of doing control design of an estimator plus a controller simultaneously, that's a well-known problem. It's called the output feedback controller. So say simultaneously. Or more generally, a feedback controller that takes the sensors as input. This is the output feedback problem. Right, so just to be very clear, what we're doing right now, we have some plant which has some sensor readings coming out. It has some internal state, X, but we don't actually get to measure X directly. We get to measure some noisy sensors potentially. So we've sort of implicitly assumed here, well, that in simulation or in modeling, we can just get access to the state directly. But in general, we have some state estimation going here, which is going to give me an estimate of the state, which I throw into the feedback controller. Which gives me my U, right? That's the sort of loop we've been assuming. We've mostly not focused on this because there are other courses that focus a lot on that. But that's sort of been implied, is that if you go to implement it, you're going to have to somehow get your state, estimate your state from the noisy sensor readings, right? The output feedback problem is, in the most general sense, designing a controller that takes and goes from Y to U, and of the solutions, of the techniques we have for output feedback design, there are, of course, any of the tools that we use in class could in some way maybe be put to task to try to do output feedback, but it's sort of surprising how few results we have, rigorous results we have about designing controllers of this form. Okay, even for linear systems, this is considered an open problem. Let me be clear, okay? So you could think of the one result we have in the output feedback world is the shining result sort of is LQG, is the linear quadratic Gaussian, which says we do an EKF, or just a Kalman filter here. You do a Kalman filter to get X hat, and then you do LQR to get U. This is optimal output feedback for the special case where you've constrained the number of states in my controller to be the same as the number of states in my plant. But you have to think of this, so the Kalman filter has its own internal state. My point is just that this is a subset of the output feedback control problem. It's one example that where we know how to solve it for a linear quadratic Gaussian system, but actually even linear systems, this is hard. If you asked, for instance, if you asked me to design the best controller, which is just a simple linear controller of the sensors, a linear feedback on the sensors, This is the static output feedback. I don't know how to do that for a linear system here. It's sort of shocking how few results we have here. LQG is the one example. And it happens that for linear Gaussian systems, if you're willing to have exactly the same number of states in my dynamic controller as my plant, then I have a Kalman filter plus LQR as a solution. And so that has justified us, in some sense, thinking about only feedback for a while. But really, there's hard problems that remain, okay? Now, I want to talk today about methods that could potentially design output feedback controllers for us, okay? But let me first convince you that even, why we should care, right? Okay, so we know that this is only optimal in the linear Gaussian sense and we could potentially do better. I mean, there's other reasons to care too, right? So one of the ones that's come up recently for us, especially for Ani and me, we've been talking to biologists about how birds fly through forests and things like this, right? And similarly, of people studying simpler insects flying through obstacle fields and things like this, okay? Experimentally, if you look at how these guys fly through obstacles, a lot of times their control decisions can be modeled very well with very simple feedback laws. I think the biologist's view of what's happening when a fly is navigating a forest is they see some things over here looming, they see optic flow over here, so they go this way. Or they see something over here, so they go this way. And it's a very simple, sensor-driven, sort of reactive control strategy that can really, could be written down in very simple static output feedback form and can describe nicely the performance of a lot of these animals, which, frankly, is still better than most of our robots, right? So maybe there's something to it, okay? And I just think that, in general, this path here of going through the state estimate and through full state feedback is not always the right path. I mean, there's just places where if I am a bird flying through a forest, right, I don't really need to know my global position in the world. I don't really need to know what's going on over there. I don't need global state information to make my decisions, and I shouldn't. And my controllers are more frail because of it. So I think ultimately, when we get good at robustness, I think controllers that are more like this will pop out. Now, of course, an output feedback controller that is allowed to have state is a superset of the static output feedback. So these are always going to be better than static output, or at least as good as static output feedback. But somehow I just feel like we're putting artificial requirements to estimate state, have a dynamic model into our systems that don't need to be there. Okay, so let me give you. The other reason to do it is that there's some times where we just don't have a good model. Period. Right? There's some systems where I can't describe in a useful way. Starting from physics, starting from the Lagrangian equations of motion, is sort of not the best way to get to a controller for my problem. And that's what I want to talk about today with some of the learning controls. The learning control techniques we're doing today are going to be a different approach to try to get this sort of directly, not by a model-based approach, but directly searching over the set of control policies that would map me from sensors to actions. Okay, and it's a fundamentally different approach. I personally think that when you have a rigid body system that has n links, even if n is fairly large, then there's so much structure in that you should really be using model-based tools, and that's why we spent almost all the term on it. But there are some great problems there where it's not the right way to start. And my favorite example of that is in fluid dynamics. Okay,